Hello, everybody. Thanks for joining me today as we go over ME166 Spring 2023 final exam. I hope you're having a good day as you watch this video. And if you're studying for this at this point, you probably already had your spring break. I hope your spring break has gone fairly well and that you're excited for the summer coming up. I know that as we're reviewing this problem set right now, I have a few exams coming up on Monday and Tuesday, notably Physics 272 and Linear Algebra. So if you're in the same boat where you're kind of stressed and you're cramming, just know that I'm there with you. Let's go over question 1. And I've already made some annotations here, so just keeping those in mind. Choose the picture which best represents the curve defined by the following equation in polar coordinates. R is equal to 3 sine of 4 theta, where theta lies between 0 and pi as our boundary theta values. So there's not really a better way to go about it in such a short time than just to plug numbers in and then plot their outputs on a graph. So let me just remind you of how to define a polar coordinate based on r and theta. We should remember that polar coordinates, like Cartesian coordinates, rely on an ordered pair, but the units of the ordered pair is different now, or are different. In Cartesian coordinates, it would usually be x and y, but in polar coordinates, it's actually defined as the radius or the distance away from the origin and theta, or the angle at which that radius line is at relative to the horizontal x-axis. So let's take, for example, that our data point in polar coordinates would be 2 and pi over 4. Well, we know that this is 45 degrees, and this is just radius of 2. So to plot this ordered pair in polar coordinates, it would simply be, okay, a radius of 2, and then rotated 45 degrees about the origin. That's a little more than 45 degrees, but rotated about 45 degrees, our point here would be this point right there, highlighted in red. Why? Because it has a radius of 2 and an angle relative to the horizontal of 45 degrees. So that's pretty much how you define a polar coordinate. And then what we're going to do is we're just going to apply that a bunch of different times as we plug and chug different numbers. So what I'm planning to do for this problem is simply to take, I think, small enough intervals of theta between 0 and pi. So we'll say intervals of pi over 8. And so we're going to plug in theta values of like 0, pi over 8, 2 pi over 8, 3 pi over 8, ... all the way up until pi. And then along the way, we're going to plot out each of the outputs that we get corresponding to our theta values. So we're going to start with that. I'm going to form a very improvisational, either one. I'll go with a provisional table here where theta is in and then r is out. So we'll start with theta is equal to 0. From that, we get 3 sine of 0, which would be equal to 0. Okay, and actually I'm going to do all 8 of these, or 10 of these, 9 of these data points now. Pi over 8, that would be 3 sine of pi over 2. That would be 1. Okay? Oh, sorry, that would not be 1. That would be 3. We have 2 pi over 8. That would be 3 sine of pi over 4. That would be pi. That would be back to 0. Then we do 3 pi over 8. I'm shifting how the fraction looks so we have more space to work with. That'd be 3 sine of, what is that? 3 pi over 2. That would be negative 3. And then this process continues over and over again until we reach the upper bound of pi. So this would be 4 pi over 8. This would be 3 sine of, what is that? 4 pi over 2, 2 pi. That would again be 0. And I'm going to take a stop for now, and let's just plot out the 5 points that we have, just to give you an example of what we're doing here, and then we'll finish out the rest of the remaining 4 points. 4, right? Yeah, 4 points. So let's look at our first data point here. We have a theta of 0 and a radius of 0. Well, if that's the case, then our first point would be located here at the origin because it has a radius of 0. Now, for theta equals pi over 8, that would be located, that would have a radius of 3. Well, we can approximate the theta value to be somewhere along this line, and that would have a radius of 3. And we can approximate the curve in polar coordinates to follow some sort of curve like that, just based on the properties of polar curves. If you measure all of the angles between 0 and pi over 8, you could find that it follows a trajectory like this. Okay? And then as it hits this, we'll have to see actually first. So now we look at 2 pi over 8. We plug that in, we get 0. So we know that it has to return back to the origin, so it would follow a curve like that, returning back to r equals 0. Then it goes to 3 pi over 8. We do 3 sine of 3 pi over 2 is equal to negative 3. Well, 3 pi over 8 would be located maybe around there, probably. Now, the key point is that our output here is negative. So if we originally would plot along this direction, we're going in the reverse direction since we are plotting a negative number or a negative radius. So our fourth point would be maybe around there. And of course, following polar curves and the nature of polar curves, we would have to curve our way to that point. Just like that. Now 4 pi over 8, it goes back to the origin, back to 0. So we simply draw back to 0 like that, and we can start to see our curve form a little bit. And now, from this, we can already eliminate a few answer choices. First of all, it surely cannot be that one, because that doesn't look like anything. You can already approximate or eyeball here that this reaches like its peak or its largest value at theta equals pi over 4, and by that nature, it doesn't look anything like our graph. Now, this one obviously is not correct as well, because this does not include this pedal right there, so we already know that's wrong. And now we're left down to 3 answers left. Let's continue plugging in answers until we get to theta equals pi. 5 pi over 8, we get 3 sine of, what is this? 5 pi over 8, 5 pi over 2. And that would be equal to pi over 2, again, which would be 3. 6 pi over 8 would become 3 pi over 4. That would be 3 sine of, I can probably just keep adding pi's over 2's, probably. That's the trend I'm seeing right here. So I'm going to add another pi over 2 to 5 pi over half. I would get 6 pi over 2, I would get 3 pi. That would become 0. So 7 pi over 8, I do the same thing. 3 sine of 7 pi over 2. That would be equal to negative 3. And then finally, pi 3 sine of 4 pi would be equal to 0. And with that, we can plot out the rest of our values here. So we were last left off looking at this curve, or this part of the curve right there. So we're left off at the origin. Let's continue. So 5 pi over 8, 5 pi over 8 would be past the 90-degree angle line. It would be like somewhere along this line right there. So 5 pi over 8, that would have a radius of 3. That'd be like right around there. And then we're going to simply draw the curve to that point. Now 6 pi over 8, it returns back to 0, so we don't need to worry about that. 7 pi over 8, it's plotting along somewhere like this line. So you can do... Oh, sorry. I should probably explain what I just did here. As we said before, we see that 7 pi over 8 is the theta value. It starts out in this direction, but because it's a negative, we're going to draw it in the opposite direction instead. We're going to plot it in the opposite direction. So that would be, I think, right around there. That would be our negative 3 value. And then it returns back to the origin of pi, which would be that. And we can see that that would be our final curve, and that matches answer A. So answer A would be the correct answer for this problem. Now, those of you might be asking, how could you approximate the lines on which the angles might sit? Like, how could you determine that pi over 8 might look like, I don't know, this line. And that's all just because you can sort of figure out, it's like a slice. Let's take, for example, that we have a pizza with, I don't know what this is, a pizza with 8 slices, right? Or a pizza with 16 slices. We'll say 16 here. We'll add a few more slices, just like that. You know, for a second it looked like a cat with whiskers, but I think it might just be schizophrenic. So, let's take a look at this. You can determine the way that I'm figuring out, or like the way that I'm determining what the angle or the line might look like, is just by how much of the circumference I would have traveled in the distance that the theta value displaces, right? So in this case, if I travel a fourth of the circle, I've reached theta equals pi over 2, but my circumference traveled, or my arc length traveled, would be 1/4 of the entire circle, right? And in this same principle, I would travel this arc here. Theta here would be pi over 8, but the amount of arc length that I traveled would rather just be 1/16 of the circle. And if you're looking at just within this 90 degrees here, I'll draw this zone out in green. If you're just looking at this zone in green here, that would rather just be 1/4 of the zone traveled. And that's pretty much how you can approximate the lines on which the angles sit, or the lines that the angles represent. And with that, the solution to this problem has finished. Welcome and welcome back, everybody. Thank you for joining me today as we cover question 2 of this problem set. It says to consider the following two complex numbers, z is equal to 4 plus 4 times root 3 times I, and w is equal to 3 plus I, or root 3 plus I. If we consider these two complex numbers, then z over w in polar coordinates is given by any of the following 5 answer choices. Now, before we begin anything, let's review something that will be very important, or two things that will be very important to solving this problem. The first thing is Euler's identity. Now this is very important. It's actually a very beautiful formula as well. But Euler's identity says that if you have e to the power of I times theta, that can be represented as a sum of both cosine theta and then plus I times sine theta. Now, in the same principle, if you have r times e to the I theta, then that would be represented as r times cosine theta plus I sine theta. Now, I'm not going to show you the full derivation. This comes from combining the Taylor series for cosine theta and sine theta, and then multiplying the series for sine theta by I. That is how you get the Euler identity. But we're just going to use it to solve this problem. Now, the second thing is rationalizing, I believe what it's called, rationalizing the denominator. Now, this is really important for solving, or at least better representing a quotient of complex numbers. And we'll go over what that is in a second, but that's just say that any complex number, a plus bi, has a conjugate. That conjugate would also be equal to a minus bi. And the reason why that is that if you just multiply these two together, you get a plus bi multiplied by a minus bi. You multiply everything together, you end up getting something of the form a squared plus b squared I squared, or sorry, a squared minus b squared I squared. But what does I squared equal? I squared, in fact, equals -1. So your solution ends up coming out to be a squared plus b squared. So by doing this sort of step, you've taken out the imaginary component from the denominator, and you've placed it solely to be in the numerator instead. We're going to take these two fundamental concepts and apply it to solving this problem. Let us begin. So we represent this quotient literally. 4 plus 4 root 3 times I over root 3 plus I. This is where we rationalize the denominator. we do root 3 minus I, and then multiply both sides by root 3 minus I, root 3 minus I again. This top part becomes 4 root 3 minus 4I plus 4 times 3I minus 4 root 3I squared, and the bottom becomes 3 minus I squared. We're going to simplify that out. This becomes 4 root 3, hang on. This specific part becomes, that becomes positive 4 root 3, and this bottom one becomes negative 1, and that which becomes positive 1. Now, knowing this, we can simplify this down. This becomes 8 root 3, and then this also becomes 12. 12 plus 8I, and that would be over 3 plus 1, which is equal to 4. Our final representation of this equation or quotient becomes 2 root 3 plus 2I, which again comes out to be another complex number, but thankfully we can represent this in terms of Euler's identity. So, as you may recognize here, we have to take this formula and pull some factor or coefficient valued r out of it such that the components become equal to some form of cosine theta plus I sine theta. Now, it's pretty simple to see what that r has to be. R has to be equal to 4 in this case, because we can take 2 root 3, and then if we divide that by 4, we end up getting root 3 over 2, and then we can just reference the unit circle. Likewise, we can take 2I divided by 4, we get I over 2, or I times 1 over 2, and that can be represented by the same angle on the unit circle. So let's solve. We have 4 times root 3 over 2 plus 1/2 I. This component must be equal to sine theta. This component must be equal to cosine theta. Cosine theta must equal root 3 over 2. So theta must equal, what is it in this case? It'd be this, right? Theta must equal pi over 6. So now we've established what our theta value should be. We've established what our r value should be, which should be 4. We can pretty much go ahead and find our answer. So right off the bat, we can eliminate this, we can eliminate that, we can eliminate this, this, and this. So D, E, and C, and B are all off the list. Firstly, for these two answers, r is equal to 4, not 8. For these two answers, our theta value is equal to pi over 6, and neither of the sums found in the solution equate to pi over 6. So the last answer that could work is only answer A. Answer A is thus our solution to this problem. Welcome and welcome back. Thanks for joining me today as we cover question 3 of this problem set. The graph of the polar equation, the graph of the polar equation, r is equal to negative 8 sine theta is, and then we're given 5 answer choices to choose from. So let's go over the principle of what a form coefficient times sine or cosine theta actually represents. So we're going to start with the case of r is equal to some form d cosine theta. Now, the reason why it's labeled d will be much apparent later as we continue solving this problem. If we have a circle of form r is equal to d cosine theta, this is what we will see. We will see a circle that stretches out into the right or into the left, depending on if d is positive or negative, and the diameter of the circle would be equal to d, which means that the circle would be centered at a point d over 2, 0, where this is the x component, that's the y component, so this is in Cartesian coordinates. And the same thing would apply for this example here. That includes the sign. It'd be like negative d over 2, 0, whatever, right? Now, importantly, remember that sine theta is just equal to cosine theta plus pi over 2. So it's been shifted by 90 degrees. So you can imagine that a circle representing d sine theta would just be this red circle here, just shifted 90 degrees, or rotated 90 degrees about the origin. Which means that a circle of form r is equal to d sine theta would be a circle spanning out into the y-axis, above or below the x-axis, and the same principles apply, where the diameter of the circle, where d is the diameter of the circle, and that the point is centered at some point 0 comma d over 2 or 0 comma negative d over 2, whatever, right? So we can use these principles to end up solving this problem here. So our original equation of this problem is r is equal to negative 8 sine theta, which means that this circle would span outwards into the negative y direction below the x-axis, because d in this case is negative, so all your values are reversed. Thus, we know that that circle must be centered around 0, comma, d over 2, where d is negative in this case. So it would be 0, comma, negative 8 over 2, and that turns into 0, comma, negative 4. We also know that if negative 8 represents the diameter, then the radius must be equal to d over 2. The radius is equal to negative 4. Now, obviously, having a negative radius is pretty stupid, so we're gonna pretty conveniently take the absolute value of that and just consider its positive representation, which would be 4. And knowing these two pieces of information, we can answer the question. It must be a circle of radius 4 centered at 0, comma, negative 4. All these other answer choices would then be wrong. Welcome and welcome back, everybody. Thanks for joining me today as we cover question 4, which asks us to find the area between the curves defined by the polar equations r is equal to theta, e to the theta over 2 power, and r is equal to 1, where theta is between 0 and 1 inclusive. So for this type of problem, we just need to figure out, or actually for any bounded area problem, we need to figure out which curve is going to be larger than the other curve. In a problem like this, they will never give us an example where one curve will be larger than the other curve, and then will be smaller than that other curve between the domain that we're given. It'll always be that one curve is always larger than the other. So we're going to look at r is equal to e to the theta over 2 power, and we're going to look at what the minimum value of e should be. Well, it's pretty clear to figure out what the minimum value of this function might be. It would just be equal to 1. If you consider an exponential function is always growing. And if you plug in 0, it would be equal to whatever coefficient is multiplied out here by, e to the theta over 2. In this case, our coefficient would just be 1. Thus, the minimum value of this first function must just be 1. If the function thus keeps growing then, in value, that means that e to the theta over 2 is always going to be greater than r is equal to 1, for at least the domain that we're given. And from that, we can begin solving this problem. Okay, so let's consider how we're going to find the area of each of these functions represented to be in polar coordinates. Well, we're going to take a look at just a standard circle here for now. Let's take a look at the circle. And I wanted to find the area of just this slice right here. Well, how would you end up doing that then? You would take the full area of the circle. If the circle has a radius r, the full area would be equal to pi r squared. But then you would say, okay, but I only want to have just this part of it, right? Now this part is represented by the angle of theta. You can represent it as a fraction or as a percentage of the area of the entire circle. Now that percentage, or that coefficient, will look to be something like theta over 2 pi, because it would be the percentage of the area that you want over the total percentage of the area. So we're going to put that in. Multiplied by theta over 2 pi. And we see that the area of just this one sector would be theta r squared over 2. Now, if you bring this down and remake it or recalculate such that you're finding a very, very small sliver of area, that would become d theta. This becomes r. That becomes r. And this again would be d theta here. Well, now your very, very small sector of area, or area of that sector, would be r squared over 2 d theta. Now you can take this very small slice, or this formula for a very small slice, and you can use it to find the area of any profile. The reason for that being that at this very minuscule size, or very, very thin slice, you're not considering like the curvature at that point, or like at this point right here. Even though it is a very sharp curve, your arc length here is going to be so small that you can just represent it as having a constant radius. That's pretty much it. So we're going to use dA is equal to r squared over 2 d theta to calculate the area of any polar curve that we need to find. In this case, we're looking for the area of a polar curve. R is equal to 3e times theta over 2, and r is equal to 1. We know that r is equal to 1 is just a circle centered at the origin of radius 1, and we know that e to the theta over 2 starts here because when theta is equal to 0, this function here is equal to 1, and then it just continually gets larger and spirals pretty much out of control. And now we're looking for it probably only between this area right here, so we're just looking for that sliver. I'll highlight this sliver in blue. We're looking for that sliver. But enough about visualizing it, let's actually start solving it. So, it would be an integral, just one integral, from our lower theta value all the way up to our upper theta value, and it would simply be that we take the area of the larger function and then subtract it from the area of the smaller function, and then we would find the area bound between those two curves. So the area of the bigger function would be 1/2 multiplied by our bigger squared d theta, and then minus the integral from 0 to 1 of the smaller area, r small, squared d theta. Now we know that r big is just equal to e to the theta over 2, and the smaller is just 1. So we can do that. That would be 0 to 1 of 1/2 multiplied by e to the theta over 2 squared d theta, and then minus the integral of the integral from 0 to 1 of 1/2 multiplied by 1 squared d theta. You can combine these integrals into one integral from 0 to 1 of 1/2 e to the theta over 2 squared, and then minus 1 squared d theta. Now some simplifications are to be made to solve this problem. We have the integral from 0 to 1 of 1/2 times e. Follow your exponential rules here. You have theta over 2 to the 2 power. That would just be theta over 2 multiplied by 2. That would be e to the theta, and then 1 squared. That's pretty difficult. That'd be 1, I think. Right. And then from there, we distribute out. We get 1/2 e to the theta minus, no, we don't even need to do that. We bring the constant 1/2 out of here. 1/2 goes out. The integral from 0 to 1 of e to the theta minus 1 d theta. That'd be 1/2 multiplied by e to the theta minus theta from 1 to 0. That'd be e, or 1/2, multiplied by e minus 1 minus 1/2, 1 minus 0. That'd be 1/2 e minus 1 half minus 1 half. That would simplify out to become 1 half e minus 1. This would be your final answer. Is that anything here? Yeah, that is. That would be this one. Reason being, you can multiply everything, or if you do this, you can multiply everything by 2 here, or you can combine it into one fraction, not multiply everything by 2. So you bring the e half, or you bring the e into the 1 half, and then you have minus 1 half. Sorry. E over half. No, sorry. E divided by 2 minus 1. But 1 can be rewritten as 2 over 2. You have e minus 2, and then both of those are over 2. That becomes e minus 2 over 2. So thus, the equation is solved. Question 4 is complete. Hello, everybody. Thanks for joining me today as we go over question 5 of this problem set. It asks us, or it tells us, that the equation of an arbitrary plane is given by 3x minus 8y plus 4z is equal to 17. We are tasked with finding which of the following vectors that is parallel to the plane. Now, if it wasn't clear, this is the equation of the plane. Now, to really get this question, let's figure out how to actually define the equation of a plane. So, in space, let's say that there's a vector, a very random vector n, whose entries are a, b, and c. We can't change the values of a, b, and c, so they're just constants. Now, let's consider a second vector here, x. Now, this will be our input vector. This is the vector that we can just plug numbers into space, and then we can plot the vector however that we want it to. So if that's the case, then if it's controllable, then it's x, y, and z. Most importantly, because we're the ones that control the values of its entries. The plane equation just asks that if I have this n vector here, what is every vector in three-dimensional space that is parallel, or no, not parallel, perpendicular to this n vector? That's just to say that if I dot it, if I do the dot product between n, this vector, and x, my input vector, what are all the vectors such that that dot product is equal to 0? If we do that, let's remind ourselves of how to do the dot product. If I have two vectors here, a, b, and c, and I have x, y, and z, the dot product is done by simply multiplying each of these products here and then summing them together. So this would be ax plus by plus cz, and that sum must be equal to 0. So it's pretty clear then that this is a vector that we're going to define this vector n to be the normal vector to the plane. If it's the normal vector to the plane, then that means that all the vectors on the plane must be perpendicular to this normal vector. That's all to say that our job is to take each of these vectors, take the dot product with our formed vector n, and determine which one has a dot product of 0. That is going to be the one that is perpendicular to the normal vector and thus parallel to the plane. So let's define out our normal vector here. It's pretty clear then that the coefficients of our normal vector will be a, b, and c. A, b, and c in this case correspond to values of 3, -8, and 4. Now all we need to do is just take the dot product of each of those. So the first one we're going to do is 1, 2, -1. 1, 2, -1. I write it out here. To remind you, the dot product is just multiplying each of these two entries, the parallel entries in the two vectors, and then summing them together. So in this case, it would be 3 multiplied by 1 minus 8 multiplied by 2 plus 4 multiplied by 1. That would be what? 3 minus 16 minus 4. That is definitely not equal to 0. We move on. The next vector to look at would be 3, -8, 4. Now, you can already tell that this is not going to be parallel because it's the same vector as the normal vector. So it's rather going to be parallel to the normal vector instead, and not to the plane. We're going to look at the third vector. Actually, before I do that, I'm going to cross out these first two answers. The third vector is 0, 1, 2. If we dot that together, we get 3 multiplied by 0, minus 8 multiplied by 1, plus 4 multiplied by 2. We get negative 8 plus 8 would be equal to 0. So this one looks like one that we can actually use, but it's always good to never leave out the last answer that we have not checked yet. So we're going to check that quickly. The last vector is 2, 1, 0. We dot that with our normal vector. We get 3 multiplied by 2 minus 8 multiplied by 1 plus 0. That would be 6 minus 8. That'd be negative 2. That would not be parallel to the plane. And that would likewise not be our answer. So you can pretty much see that C would be the answer to this problem. And since we have an answer, E is not an answer to the problem either. Hello, everybody. Thank you for joining me today as we go over question 6. Let's begin immediately. Find the volume of the parallelepiped where the following 3 vectors correspond to the 3 sides of this shape are given by, which by the way, there's actually a typo in here, which I cannot believe. It's corresponding with a ding 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 at the end of correspond instead of just correspond. Otherwise, the sentence does not make sense. With that being said, let's begin solving this problem. This problem of volume will require both a cross product and a dot product. Let's say that I draw out my shape here. I will stop calling it a parallelepiped because that is a giant mouthful and I'm too lazy to say that all. And I think, by the way, every time I think of parallelepiped, I think of the word paraplegic. And I know it's a little bit random, but it just comes to my head sometimes. So let's draw out my 3D object here. It will look something like that, right? The idea is it's pretty much just a parallelogram projected into 3D space. That's all that this is. Now, to find the volume of a usual parallelogram or parallelepiped like this, it would still just be the base multiplied by the effective height of this object. Now, the way to do that with vectors would first be to do the cross product to find the base, to find the area of this base. The cross product will say, I'm going to take these 2 vectors here. I'm going to operate on them in such a way that I can find the area encapsulated between the parallelogram formed by these 2 vectors. Now, with this cross product, it's lucky for us that it's been defined in such a way that it sticks perpendicularly out to these 2 vectors defined below, and its magnitude is also the area encapsulated within these 2 vectors. Now, that would just find the base area, though. We need to actually find the volume. And that's where this third vector would come into play. We can assume, or we can kind of guess, that it requires a dot product because let's say that this vector was very not parallel to our area vector. Well, then the volume of this shape would actually be much less than if it were more parallel with our area vector. If it were more parallel, the area would be more maximized, which is why we can kind of guess that it needs a dot product. So we can split this up into 2 operations then. I'm going to define each of these vectors as v1 for OA, v2 for OB, and v3 for OC. Our first step is the cross product. The cross product requires a matrix form where the top row is elementary vectors I, J, and K, and the bottom rows, or the bottom 2 rows, would be the first vector v1, 1, 1, 1, and the second vector v2, 0, negative 1, and 1. I'm going to write out the cross product as I would do it in linear algebra, and then I'll explain it to you. I would take ijk and I multiply it with this small matrix in here, 1, 1, negative 1, and 1. Then I will subtract it from j, multiply it again by the combination of this vector and that vector. That would be 1, 1, 0, 1 to form its own matrix. Then plus k multiplied by this smaller matrix here, 1, 1, 0, and then negative 1. Now, with everything written out, I will employ something called the determinant. Assuming that you have not taken linear algebra and you do not know what the determinant is, that's to say that each of these smaller matrices, they have an area associated with them. The area of the vectors between the vectors contained within this matrix can be found by multiplying the first entry here by its diagonal entry and subtracting that by this entry multiplied by its diagonal entry. So for the example of I, that would be I hat is multiplied by 1 times 1 minus negative 1 times 1. I'll employ the same thing for the rest of them. That would be minus j hat 1 times 1 times 1 minus 0, and then plus k hat, that would also be negative 1 times negative 1, and then minus 0. So then we have I, which would be 1 plus 1, that'd be 2, minus j, that would be 0, nope, sorry, that'd be 1, and then plus k, that would be negative 1, right? And so these elementary vectors, we can't simplify them down any further because they're not really numbers. They're actually regular vectors. So I, in this case, would just be 1, 0, 0, or a vector representing motion in the x direction. J would be 0, 1, 0, representing motion or direction, or representing motion or value in the y direction only. And then K would be 0, 0, 1, representing motion or value in the z direction only. And then by combining all three of these, you can pretty much access every point in 3D space. That's the idea. So this vector can be written out to be 2, negative 1, and negative 1. And then from there, we need to take V3 and dot it with this area vector that we found here. I will appropriately define it to be A. Let's perform this operation, A dot V. To remind you, the dot product of two vectors is just, if I have A, B, C, actually I'll write out the values themselves. That'd be 2, negative 1, negative 1. And then V3 in this case would be what? 1, negative 1, and 0. The dot product just says, I'm going to take the x entry in the first one, multiply by the x entry in the second one, take the y entry in the first one, multiply by the y entry in the second one, the z entry in the first one, multiply by the z entry in the second one, and simply sum all those products together to form your final dot product. Let's do that. This will be 2 times 1 plus 1, not even 1, negative 1 times negative 1, and then plus negative 1 times 0. That would become 2 plus 1. Pretty hard calculation. I'm in a few seconds for this. That'd be 3. Okay. So that would be our answer then. We figured out that the volume for this parallelepiped, or this shape, should just be 3 units. And we see here that 3 is an answer. 3 would correspond with answer C. Hello everybody, welcome and welcome back. Thanks for joining me today to cover question 7. Find the area of the region bounded by the curves x equals 3 plus y squared and x equals 7. Well, first thing we're going to do is we're going to underline some key information here. This and this. So, second thing we're going to do is draw out a diagram and then hopefully visualize what's happening here. And I encourage you to do that whenever possible on the exam because that really helps check your work to make sure you're not tossing out the incorrect formulas to use. So we have our x and our y-axis here. We know that the function is no longer dependent on x, it's now dependent on y, which means the y-axis is now our independent variable, and the x-axis is the one along which the outputs will produce. So for example, this parabola x is equal to 3 plus y squared. Well, it still has a positive intercept, but now it's dependent on y. So maybe this parabola would open out horizontally like this to the right because it opens out in the positive x direction. As would a parabola depend on an x open out in the positive y direction. So that might be our parabola. Now, x equals 7 here, well, this is just a vertical line as we know, centered around x equals 7, like so. And the region that we're asked to solve around becomes pretty apparent. It is this region in here. We are going to define a few things here. Firstly, we need to find which function is the greater function and which function is the lesser function within this region bounded by these two intersection points here. So be this region right around here. We can see that our lower function, xl, must be equal to the parabola 3 plus y squared, and our greater function, xu, must be equal to 7, or the vertical line. The next step, then, is to figure out what the bounds of intersection are, because as we can see, these bounds of intersection actually help to define where our region ends and where our region begins. So, what we need to do here is set up an inequality. For all values of y that we're looking for, the greater function must be greater than the lesser function. In other words, xl must be always less than xu for all the values that we're looking for. We plug that all in, we get 3 plus y squared must be less than or equal to 7. We get y squared must be less than or equal to 4. And then from here, we get y must be less than or equal to positive or negative 2. Just by the way that square roots work, if you take the square root of a squared number, this becomes, or you can simplify this inequality down to negative 2 must be less than or equal to y must be less than or equal to 2. This defines our bounds of integration along which we will solve this problem, or along which we will. All right, now the next step is to actually solve for the integral. So, as you'll probably recognize, you can split this up into two separate integrals, which can be combined into one. You can say first that I want to find the area under the very large curve, or the much bigger curve, which would be the vertical line, and then subtract that from the area under the smaller curve, which would be the parabola, and that will help me to find the area of this region that is bounded by both of these curves in the green. So this would be the first integral from negative 2 to 2 of the greater function, which is 7 dy, and then minus the area under the lesser function, which would be 3 plus y squared dy. That would be conceptually, but of course you can combine this into one integral. That would in fact be the integral from negative 2 to 2 of 7 minus 3 plus y squared dy. Now keep in mind, the only time that you can join these integrals together is when their bounds of integration are the same and when their differentials are also the same. In this case, both bounds of integration are from negative 2 to 2, and the differential of integration is dy, so we can't combine these integrals together. From here, we simplify this out. This becomes negative 2 to 2 of 7 minus 3 minus y squared dy. This becomes the integral from negative 2 to 2 of 4 minus y squared dy. And this simply uses the power rule to solve. This would become 4y minus y cubed over 3 from negative 2 to 2. I'll evaluate the upper value in red and the lower value in blue. This would become 4 times 2 minus 2 cubed over 3. And then, of course, you would subtract that, or you subtract from that, all of that, but with negative 2 plugged in instead. So 4 times negative 2 minus negative 2 cubed over 3 as such. This would become 8 minus 8 over 3. And this would become, in parentheses here, negative 8 minus negative 8 over 3. That would become 8 plus 8 minus 8 thirds. This would combine it to be a positive sign, so it's another minus 8 thirds because we bring this negative sign into there. That becomes 16 minus 16 thirds. What would that be? Well, 16, if you multiply that by 3 to make this all common denominator, that would be 48 thirds. So 48 thirds minus 16 thirds, that is equal to 32 thirds. And that would in fact be the answer to this question. That would be answer E. Hello everybody, thanks for joining me today as we cover question 8 of this problem set. If the work required to stretch a spring 2 feet beyond its natural length is 18 foot-pounds, how much work is needed to stretch it 4 inches beyond natural length? Now bear in mind that this is inches and not feet, because that might get some people tripped up on this problem. But with that being said, let's begin looking at how a spring might work. in terms of how much force it exerts, the work that is done on it, and then using these principles to solve the problem. Let's say that I have a spring here. We'll define the left end of the spring to be the origin and the right end of the spring to be a value x0. Now, this can be defined as a length L0. L0 is to say that this is the length of the spring when the spring is at its lowest potential energy. That means it does not want to do anything. It's already feeling at its most comfortable. This is like if I'm in bed and I don't want to do anything because I feel at my most comfortable. I am at my lowest potential energy. That is the same thing with the spring. However, what we can do is we can compress the spring by a distance negative delta x, or by a positive distance we extend it a positive delta x. And we can measure the force that the spring exerts back on us as we compress it or as we pull on it. What we find then is that the force scales linearly with the displacement. It will look something like that. Now, the slope of this force graph is dependent on how much the spring is resistant to your motion or to your direction of pulling or compressing. So if the spring is more resistant, the slope would be higher. But if the spring was less resistant, the slope would be lower. And then from here, we can define that resistivity or that resistance measure as a value k called the spring constant. This means that we can define our function of force with respect to x, or displacement, as k multiplied by x. And then from here, we can solve for the work done on the spring as you pull or compress on it. So let's say, well, we know that work in any scenario is always the integral from your starting position to your ending position, and then multiplied, or that would be the function of force at every point x, and then with respect to dx, because that's the motion that you're that's the direction that you'll be moving in, or that the spring is being pulled or compressed in. So that's the direction of work. Bear in mind this only applies for a spring. There obviously are other cases, but for springs it'll always be this, right? So from x0 to xf, where the function of force is kx dx, this is simple power rule integration. That would be 1/2 kx squared from x0 to xf. That would become 1/2 k xf squared minus 1/2 k x0 squared. Just like that. So this would be the work done on the system as you pull it from a distance x0 to a distance of xf from equilibrium. So we can use this to solve for what we're looking for in this problem. The first scenario, we're given that the distance x0 would just be 0, since it is from natural length. And the final distance pulled, sorry, let me write this out again. And the final distance would be 2 feet. Now, we're not given anything about the spring constant, but we are given the amount of work done on the system. So we know that we can use this equation to solve for the spring constant, which you can use to solve for the second scenario in this problem. We're given the work done is equal to 1/2 kxf squared minus 1/2 kx naught squared. However, this term is equal to 0, so all left with is 1/2 kxf squared is equal to the work done. I'm going to move this to the right. This would become 18 is equal to 1/2 k times 2 squared. If I sub in all my variables, 18 is equal to 2k, where k is equal to 9 units. Then from here, we can solve for the actual part of the problem using the spring constant. They actually give us everything we need to know in this scenario. Using the formula, same thing here. X naught still equals 0, since we're pulling it beyond natural length as per usual. x final here would be equal to 4 inches. Now, there are 12 inches in a foot, so if we wanted to convert it into feet, it would be 4 inches multiplied by 1 foot per 12 inches. That would become 4 over 12. That'd be 1/3 of a foot. That would be our final displacement. Then from there, we use the formula. Work done is still 1/2 kxf squared minus 1/2 k0 squared. Sorry, 1/2 k times 0 squared. K times x naught squared. We know that this term goes to 0 because our initial position is 0, but this is not. We plug in our values, so we get 1/2 times 9 times 1/3 squared is equal to the work done. Now this just becomes simplification. This would become 1/2 times 9 times 1/9. That would become 1/2 times 9 over 9, and that would simply become 1/2. So the work done on this system would just be 1/2 of a foot-pound, which is answer C. Hello everybody, thanks for joining me today as we cover question 9. I hope you're having a good day as you watch this video. Let us get right into it. Find the volume of the solid generated by revolving about the y-axis. This region, bounded by y equals 0, y equals x over 1 plus x cubed, x equals 0, and x equals 2. So let's before anything, I'm going to quickly draw out a diagram, and I encourage you to do this whenever possible on a test if you're feeling stumped, to draw out a diagram and literally visualize what you're doing. That way, it'll help you to derive the formula if you're really in a crunch. Let's say I have my y-axis here, and I have my x-axis here, like so. My curve, or my revolution, might look something like this. And it would look something like this, perhaps. Like maybe like an air hockey stick, puck, thingy, whatever, right? It would look like that. Now, what you may notice is if you try to find the volume of the solid using horizontal disks, like so, this function is impossible to integrate over because you get to a point where you have a break in the horizontal line. So this means that for each y function, or for each y value here, it presents multiple different x outputs. This fails the horizontal line test and renders this function as not actually a function, which means it's impossible to integrate over. This is where we employ a different scenario, and the way to recognize when to use a scenario is when your axis of integration is the same as the output function along which the output is generated, or the axis along which the output is generated. In this case, the y-axis is both the axis of revolve and is also the variable of the output. This is when you would use the approach of the shell method. So what that says is you can take this solid here and you can pretty much split it into an infinite amount of very thin cylindrical shells radiating outward from the origin. And then you can take the very, very small volumes of those. So if I blow up this cylindrical shell, you'll notice then several key things. You'll notice it has a very, very thin thickness here. We can call this thickness to be our differential variable, dx. It also has a height. That height would just be the height of the function at that value, f of x. And then it also has a radius extending from the origin. But if the radius extends from the origin, then the radius can just be written as x, the value of x. From here, it just comes down to figuring out how do we actually find the volume of this solid. Well, a nice way to think about it is by taking a very small profile here. This would be a rectangular profile with a width of dx and a height of f of x. The area of this profile is equal to f of x multiplied by dx. The next thing you do is you simply revolve that about the circumference of the cylinder, which means that you would multiply it by a value of 2 pi r. So then your volume here for this one cylinder would be the circumference multiplied by the area of that one profile. That would be 2 pi r multiplied by f of x times dx. And that comes out to be 2 pi of x multiplied by f of x times dx. That would be the formula of the volume for one cylinder only. And then to turn this into an integral over the entire function, you would simply put the integral sign on both sides and then integrate. But we're going to do that in this step right now. So we know what x is in this case. X is just x, and the function f of x is just, well, this function here. Y is equal to 1 plus, y is equal to x over 1 plus x cubed. So let's start solving this integral, or let's start setting it up. We have from, what is this? From 0 to negative, from 0 to 2, following our lower and upper bounds of integration. We have 2 pi x, and then multiplied by the upper value of y. It would technically be this function here, x over 1 plus x cubed, minus this value here. But since it's y, the lower bound of y is equal to 0, you can just write that off to be that the value of y, or the value of x here, would just be x over 1 plus x cubed. So I'm going to write that in, x over 1 plus x cubed, and then that would be with respect to the dx. What you'll notice right off the bat is you can actually turn this into a very nice u substitution. I can bring out the 2 pi. This turns into x squared over 1 plus x cubed dx. The u would be on the bottom here. We call u equal to 1 plus x cubed. We see that du with respect to dx would be 3x squared. We can turn that into a function dx to be in terms of x and du. That would be dx over du is equal to 1 over 3x squared. That would eventually mean then that dx is equal to du over 3x squared. This equation dx can be substituted back into our original integral to allow for a change of basis here. Now keep in mind then that if we are changing the bounds of integration, if we are changing the basis from x to u, then we must change the bounds of integration to be in terms of x, or from being in terms of x to becoming in terms of u. That's pretty simple then. We just plug in the values of x from our bounds of integration into this function here, and then we solve for u. So for example, u, when x is equal to 0, would just be 1 plus 0 is equal to 1, but u, when x equal to 2, would be 1 plus 8 is equal to 9. So those would be our new bounds of integration, and now we are ready to solve in the new basis. So we have the integral from 1 to 9 of x squared over u, and this would be with respect to du, but over 3x squared. Now you notice then, these cancel out. We still have the 2 pi out in front. This would become 2 pi multiplied by 1 over 9, the integral of du over u, or over 3u. I'm going to bring the 3 out though, so it becomes 2 pi over 3 multiplied by this integral. And you'll notice this is just the natural log. So this would become 2 pi over 3 multiplied by the natural log of u between 1 and 9. We plug everything in, we get 2/3 multiplied, 2 pi over 3 multiplied by ln of 9 minus ln of 1. But then you notice that ln of 1 goes to 0. So this just turns out to be 2 pi over 3 times the natural log of 9. And that would be our final answer. Is that an answer here? That would in fact be answer D. Hello everybody, thanks for joining me today as we cover question 10 of this problem set. The graph of f of x is equal to e to the x plus e to the negative x on the interval -2 to 2 inclusive is revolved about the x-axis. Find the right formula that describes the area of the surface generated. So I'm going to start with a very, very quick diagram to go over what we might consider when finding the formula, and then we're going to actually find which formula is correct. This will be a very heavy problem, so let's say that I have something here, a small profile, it looks like this, right? You can imagine that is revolved about the x-axis. is the idea. Let's take one of these small strips of arc length along here. I'll blow it out just a little bit. Actually, no, I don't need to. The arc length, or sorry, this small arc length right here has both a component of dx and a component of df. dx is the small change in our step, and in our step, df is the change in the function. This little arc here, ds, can be written or approximated to be the Pythagorean theorem using df and dx, df squared plus dx squared. That's pretty simple though, that's just arc length. This will come in handy in just a moment when we consider that we have to revolve this profile about here and sum up all these individual surface areas of this one cylindrical shell. That would look something like that. Now, in order to revolve it about the x-axis, then, we need to know the radius of this sort of cylindrical shell. So if I draw this out a little bit to make it a little bit clearer, it may look like this, right? This is the center. This is which the x-axis passes through, so it looked like this. And then that means then that the radius, the approximate radius of this cylindrical shell would just be the value of the function itself, f of x. So the idea is you can take the base, or you can approximate this to be some form of cylinder, like such, and then the cylindrical profile is just taking, or the area of the cylindrical profile would just be taking this one profile here, and then multiplying that by 2 pi r, or in other words, revolving it about the circumference. That is the idea. Which means that the small amount of surface area of one of these cylindrical shells, dA, would be 2 pi r, or 2 pi times f of x. F of x substitutes r in this case, or the radius of this cylindrical shell, and then multiply that by ds, or the arc length. You can kind of consider it as your circumference is the base curve, and then you're applying thickness to that base curve, right? So ds in this case would obviously become df squared plus dx squared. But as you know, with arc length, you can reduce that down to become dA is equal to 2 pi f of x. This becomes times square root of f prime of x squared plus 1, and then have a dx out in front. So this would be the area of one of these cylindrical shells, and obviously to do the entire shape, you would integrate both sides, starting from x0 all the way up to the x final on both sides. So let us use what we have here and then solve for which one of these formulas might be the correct one. As you may notice then, we need to find both f of x and we need to find f prime of x. We already know what f of x is. f of x is equal to e to the x plus e to the negative x over 2. What's f prime of x then? F prime of x would be, if I split this up, this would be e to the x over 2, and then plus negative e to the negative x over 2. This will become e to the x over 2 minus e to the negative x over 2. And then from there, we can start plugging everything in to this formula right over here. So our formula then would be the integral from negative 2 to 2, which is our lower and upper bounds of integration, of 2 pi fx, and then the square root multiplied of f prime of x squared plus 1 with respect to dx. This would become negative 2 to 2 of 2 pi of e to the x plus e to the negative x over 2 multiplied by the square root of e to the x minus e to the negative x, all that over 2 squared, and then plus 1. But I'm going to split this up to make it minus e to the negative x, put the 1/2 on both of them. That allows for easier expansion. And then dx. So for the purposes of mathematics here, or for the purposes of simpler calculations, I'm going to isolate this part here and only solve for that. So I'm going to bring that out back to the left side of the page. That would become the square roots of e 2x over 4. I'm just expanding this out right now like a polynomial. Actually, it'd be better to write it like this. E to the x over 2 minus e to the negative x over 2 times e to the x over 2 minus e to the negative x over 2, and then plus 1, like so. This would become the square root of e to the 2x over 4. As you can recall, if you have something like a to the x multiplied by a to the x, that would just become a to the x plus x. So you would add these two exponents together. That's the idea. And that's the principle that I'm using in this problem. So e to the 2x over 4, and then I do this multiplied by that. That would be minus e to the x minus x over 4, minus again e to the x minus x over 4, and then plus e to the negative 2x over 4, and then all of that plus 1. This becomes equals, I can make it a little bit smaller here actually. That would become e to the 2x over 4. This becomes 0, so e to the 0 is 1, minus 1 over 4th, minus 1 over 4th, and then plus e to the negative 2x over 4, and then plus 1. That becomes e to the 2x over 4 plus e to the negative 2x over 4, and that becomes plus 1/2, because this becomes negative 1/2 plus 1 would be 1/2. Now, this doesn't stop here, and it should not stop here, because as you'll see, these don't actually match any of the answer choices that we have besides this one. But this actually has a 1 in here that is not by mistake. That is intent to throw you off. What you need to do here is you can recognize that this might be able to be factored into one term that is squared by itself. And in fact, it can be. This can be rewritten as the square root of e to the x over 2 plus e to the negative x over 2 squared. That, in fact, simplifies down to e to the x over 2 plus e to the negative x over 2, taking out the square root. And as you might notice, that is in fact actually just f of x in this case. So if you re-include everything together, that would be from negative 2 to 2 pi multiplied by e to the x plus e to the negative x over 2. But then you multiply that again by e to the x plus e to the negative x over 2 dx. This would be, well, we don't even need to go any farther. We're good. That would in fact be answer choice D to solve this problem. Hello everybody, welcome and welcome back. Thanks for joining me today as we cover this problem set, Question 11. Compute the integral from 0 to 1 of x squared times dx, x squared times e to the x dx. So as you'll notice right off the bat, we have two different functions multiplied together. This should scream out to us to use the integration by parts formula. I'll write it out as IBP. IBP is just to say that you can take this entire blob and turn it into a product of a u function and a dv function. So dv in this case would be equal to ex, e to the x, but then multiplied by a small slice of motion dx. So you can say u dv, and that would then be equal to uv minus the integral of v du. Now this all is like a bunch of jargon, but as we follow through the steps, it'll be a lot more clear. This is pretty much just the reverse of the product rule. As you will remember, the product rule is, if you have f of x, gx, you do the prime of that, that would be, what is this? F of x multiplied by g prime of x, and then plus f prime of x multiplied by g of x, and this would just be the derivative of that, right? Then you integrate both sides, like so, with respect to dx, and then you start to see the formula emerge here. With that being said, we can begin by solving this problem. So in any case of integration by parts, we always want to select the power function as our u function. As you'll see on the right side of this equation, we end up actually taking the derivative of the du, and that becomes our new du function, right? If we differentiate a power function enough times, we can reduce that down to a constant value or down to 0. If we were to select the e to the x function as our u function, no matter how many times we take the derivative, it'll always remain ex, e to the x. So I'm going to bring this down. Our u function will be equal to x squared. Our dv function will be equal to e to the x multiplied by a small sliver dx. Now, following what we need to do for this formula, we need to integrate v. That becomes v is equal to e to the x on its own. And we need to differentiate u. So du dx is obviously just power rule. That would be equal to 2x. And then we move over the dx, so it becomes du is equal to 2x dx. So then we use the formula here. We see our u here is x squared. Our v here is still e to the x. And then minus the integral of, what is this? V here in this case is ex, e to the x, and then multiplied by du. Du here is equal to 2x. Very sorry about that. We had some technical difficulties. Let's continue with the problem. So as we verified here, du would be equal to 2x dx. So it would be 2x dx out in front here. And now we simply need to do this process again. Now the key thing to note is that if you ever come into a scenario where both functions can't be differentiated towards a constant value, you cannot end up switching which function is your u and which function is your dv. For example here, if I start with saying that u in this case is x squared, I pick the power function as the one which is always my u. I cannot pick then that u becomes ex. That would break the entire cycle. That would actually get you the completely wrong answer. You must stick to 1. So in this case, u would still be equal to 2x. dv in this case, in black. U is equal to 2x. dv is always equal to e to the x dx. The same thing is done. du over dx would be equal to 2, and v would be equal to e to the x. So, same thing happens. du is equal to 2 dx, and now we do the same thing. So I write everything out here again. 2x, x squared times e to the x, minus, in parentheses, our v function e to the x, multiplied by our u function 2x e to the x, minus the integral of, v e to the x multiplied by du, which is 2 dx. And as you'll notice, we have reduced the integral down to just e to the x multiplied by a constant, so it becomes possible to do with no longer integration by parts. Now, as you probably noticed, I have not included bounds in this problem. That is because I'm too lazy to write out the bounds. I'll write them out at the very, very end and we'll evaluate. So this all becomes x squared e to the x minus 2x e to the x, and then plus, this just becomes 2e to the x, and then all of that's between 0 and 1. As you'll notice then, this can be rewritten as x squared minus 2x plus 2 multiplied by e to the x from 0 to 1. So we'll start with the 1. That would be 1 squared minus 2 times 1 plus 2 multiplied by e to the 1. And then subtract that from 0 minus 0 plus 2 times e to the 0. That would be 1 minus 2 plus 2, 1 times e, minus 2 times 1. That would be e minus 2. And that returns to us our answer. The answer to this problem would be in choice A. Welcome and welcome back, everybody. Thanks for joining me today to cover question 12. Write the form of the partial fraction decomposition of the function 5x cubed plus... Okay, it's not worth my time, actually. So, let us go over a few things. Partial fraction decomposition just takes... we'll take, for example, that we have something like 2 over x minus 2, and then add that with 1 over x minus 4, right? And you have that equal to like 6. That's the idea. Well, to solve this problem, what you might do is you will combine the fractions together in such a way, like 2 times x minus 4 over x minus 2 times x minus 4, and then minus x minus 2 over x minus 2 squared, or x minus 2 multiplied by x minus 4, and that would be equal to 6, right? Technically, you've changed nothing, but what you've done is you allowed these to be combined into one united fraction. Partial fraction decomposition just says that I can take that united fraction and then split it back into all the separate remainders of the or all the separate remainders um, of its unique terms that go into making that unified fraction. So the first condition that we need to keep in mind is that to solve for partial fractional decomposition, you will have your numerator be the general solution to that specific remainder term, and then your denominator be a defined polynomial that represents one of the components that goes into making that unified fraction. So for example, this would be something like f of x. We'll define that to be the general solution over something like x squared plus 1. Now, here's the thing. In any case where the polynomial could be something like x squared, here, better yet, x squared minus 4x plus 4 on the bottom, and then some general solution on the top. Well, you can factor this to be f of x over x minus 2 squared. You are concerned, when we talk about the degree of any of these polynomials, you are concerned with what is inside of here. The highest degree inside of the parentheses. In this case, this would be 1, because x minus 2 has a maximum degree of 1. That's pretty much because you can split this into one general solution of x over x minus 2, multiplied by a second general solution of x, multiplied by x minus 2, or over x minus 2 again. That's pretty much the d. That becomes f1 of x plus f2 of x is over x minus 2. That's all to say. So when we talk about the degree of any of these polynomials, we are focused on what is inside the most simplified or the most factored version of that polynomial. The general solution's degree will always be one less than that of the principal degree on the denominator. So an example like some general solution x over x squared plus 4, well, you can't factor x squared plus 4 any less without including complex components, which means that the principal degree of the denominator would be 2, which means that the general solution on the top must include that which includes which means that the general solution on the top must be the polynomial that has one less degree than the denominator on the bottom. In that case, the polynomial with the degree 1 would just be a line. So the general form of a line would be a x plus b, where a and b are just both arbitrary or random constants or variables that we'll end up solving for later. So that would be how to write out the general solution of that. And eventually you're going to actually solve that, but we're not focused on solving that. We're just focused on writing a general form, right? That's the first idea. So another example of that might be if I have something like x cubed plus 3x plus 6 on the denominator, right? Now, I'm not a terrific guy with cubic functions, but let's assume for the purposes of this assignment that this is unfactorable, right? This would turn into a general solution that has one less degree than 3. Well, that would just be the general form of a polynomial, or quadratic function, which would be ax squared plus bx plus c, and then that would be over the original thing, x cubed plus 3x, and then plus 6. That also means then, for an example where it's just like the general solution over a degree of 1, your general solution would just be a constant value, something like a over x minus 1, which ties back into why you only consider the principal degree. Because if I had something like x minus squared, that would be a over x minus squared, or x minus 1 squared, which can be written as a over x minus 1 squared, or a over x minus 1 multiplied by b over x minus 1 as well. Right? So you can split this thing up into its lower degree terms, or the product of its lower degree terms. This is the first condition. The second condition is that if you have some form of, let's say you have, again, your general solution on top, but now you have some polynomial here. For example, I'll say x squared plus 4, and then to the 4th power, or to some exponent. Your general solution turns into, of course, the principal degree on top. So that'll be ax, or taking the general solution as described in the first scenario, that would of course be ax plus b over x squared plus 4 to the 4th. But then you do cx plus d over x squared plus 4 to the 3rd, and then plus ex plus f over x squared plus 4 to the squared, and then plus gx plus h over x squared plus 4 to the 1 power. The idea is that you start at the highest, and then you get lower and lower and lower, and you sum all those general solutions up. This can be pretty easily represented by an example here. Let's say that I have a polynomial here, x squared minus x plus 1 over x cubed. So this represents the scenario that we were shown before. Well, you can literally write this as 1 over x minus 1 over x squared, and then plus 1 over x cubed, which perfectly encapsulates what we just talked about a second ago by needing to include the denominator of all possible degrees up to our original exponent. That is the idea that we're getting at here with the second condition. So that means, for an example where we have, like, say, x minus 1 over x squared minus 2, x squared plus 1 squared, this would become ax plus b over x squared plus 1 squared, and then plus cx plus d over just x squared plus 1. The same principle would apply. So using these two conditions, or these two rules of thumb that we've established here, we can solve this enormous problem. So I'm going to take a second to erase all the work that I have here, and we can begin solving the problem. So right off the bat, we can disregard the numerator. We don't care about the numerator, okay? The numerator is worth about 5 farts in our currency of work for this problem. We only care about the denominator. We have the product of 3 different terms here. Oh, this is gonna suck. Oh my gosh. Okay. Alright. So right off the bat, you can see this is already in its most simplified form. This is in its most simplified form, but this can actually be factored out. So the cubic factoring of this, well, we can include one extra term, x minus 1, and then some additional polynomial out here. And we can already see, I'm not going to try to factor this out. I can already see in here that polynomials of some similar form are included. X squared plus x plus 1. This becomes x squared plus x plus 1. So that would be equal to x cubed minus 1, right? We're reducing it down to a product of its lowest degree terms, is the idea. So then on the denominator, we have a total of x minus 1 cubed multiplied by x squared plus 9 multiplied by x squared plus x plus 1. We're going to start with this. We can actually break this up and work on these independently, one after the other. So we'll start with the x minus 1 cubed. Of course, we care about the principal degree in here. The principal degree is 1, right? Which means that our general solution must just be a constant value. So we first have a over x minus 1 cubed. But as you remember, we need to add the sum of each of the remainders where the degree of the bottom decreases by 1 each time. So that would be plus b over x minus 1 squared, then plus c over x minus 1. So this one is done. We can cross that out. Then we move on to x squared plus 9. Well, x squared plus 9 can't be factored anymore. So that means that its principal degree is 2, which means that our general solution must be that of a line y equals mx plus b. But our m must be substituted by a variable d, and our b value must be substituted by a random variable e. So this would become dx plus e to represent the general solution over, what is this? X squared plus 9. And then we see here that we have the same scenario with x squared plus x plus 1. The principal degree is 2. So this will again become fx plus g over x squared plus x plus 1. And you can see that that is actually, let me see, there should be, okay. I'm just checking the answer choice right now. We can see that this perfectly represents the answer choice to be found in answer E, which means that E is the answer to this problem. Hello everybody, thanks for joining me today for question 13. Compute the integral shown below, the indefinite integral of 1 over x squared plus 4x plus 3 with respect to dx. So right off the bat, we should notice then that this, oh my gosh, I have this ugly steam thing here. There we go. That this can be factored. This can be rewritten as x plus 3 multiplied by x plus 1. So we turn this integral into 1 over x plus 3 times x plus 1 dx. So we have an integral whose denominator is the product of two individual terms that form a polynomial. This should be screaming out to us to use partial fractional decomposition. So, if you're a little bit confused about what partial fractional decomposition is and you just need to understand the fundamentals, you can go back to question 12. I explain it in more depth there. But with that being said, let's get right into solving this problem. We have that 1 over x squared plus 4x plus 3 can be equal to a over x plus 3 plus b over x plus 1. That is the idea. This principle is covered in the previous video as I just discussed a second ago, so I will not take any more time to discuss that here. We can multiply everything out by this cumulative denominator here to cancel out all the fractions. That become a is equal to x times a times x plus 1 plus b times x plus 3. Now, what we can do here is we can just plug in certain x variable or certain x inputs to cancel out one of these terms. So for example, I can plug in x equals -1 to cancel out the a term because -1 plus 1 is equal to 0. So when I plug in -1, I get 1 is equal to just b times -1 plus 3. That would become 1 is equal to -2b, or not 2b. That means that b is equal to -1/2. I can do the same thing for a. 1 is equal to, I can plug in -3 here to cancel out the b term. Then I get a is equal to multiplied by -3 plus 1, and then plus b multiplied by 0. That means that 1 is equal to a times -2. That means that a is likewise equal to -1/2. That means that we've pretty much solved these two. Oh, good catch here. This is 1 is equal to 2b. That means that b is equal to +1/2 and a is equal to -1/2. So then from there, we've pretty much decomposed this into its constituents. Now we're going to begin solving for this integral. So we have the integral of a over x plus 3 plus b over x plus 1. What I've done in this case is I've said that I can take this, and since this is equal to these summed together, that means that I can replace this box in red with these, right? That is the idea. So integral of a over x plus 3 plus b over x plus 1 dx. We've obviously found what a and b are. A in this case is -1/2 multiplied, -1/2 multiplied by x plus 3 on the bottom, and then plus 1/2 multiplied by 1 over x plus 1 on the bottom dx. This is just the sum of two integrals of two rational functions, which means that their integrals are just natural logs. So this becomes negative 1/2 multiplied by the natural log of x plus 3, and then plus the 1/2 multiplied by the natural log of x plus 1. And then, of course, since it's not an indefinite integral, that is just plus c at the end. And, yeah, we found our integral. Our integral is best represented by answer choice C. 1/2 of natural log of x plus 1 absolute value minus 1/2 of natural log of absolute value of x plus 3, and then plus c at the very end. Welcome and welcome back, everybody. Thanks for joining me today as we cover question 14 of this problem set. Evaluate the following improper integral from 0 to infinity of 2x cubed times e to the negative x squared dx. Excuse me there. So right off the bat, we should see here, we have x cubed, and, we have some sort of power function here. We'll represent that as f of x. Now we have some sort of exponential function here. We'll represent that as g of x. So this should automatically be screaming out to you, or it maybe is screaming out to you, that we should use an integration by parts formula to solve this problem. But as you may notice, this might be pretty hard to integrate. How do we get it into a form that is integrable? Well, as you probably know already, but for those that might be a little bit rough around this subject, I'll review. Integration by parts essentially says that if you have some function here that represents a product of two separate functions, one of which is u and the other of which is dv, that would be equal to u, the function itself, multiplied by the integral of dv, which is v, minus the integral of the reverse. This would become v multiplied by du. Now this formula may look out of the blue at first, but this is essentially the reverse of the product rule. As you remember, the product rule says that if you have the derivative of two functions multiplied together, that becomes u v prime plus u prime v. Then when you integrate both sides, you pretty much end up getting what is integration by parts. That is the idea. So in most cases with integration by parts, you always want to select the u function to be your power function. Because with a power function, you can differentiate it a certain amount of times such that the function's derivative or nth derivative becomes 0, or its polynomial degree reduces. If you assign the u function to become the exponential function, well, no matter how many times you take the derivative of that exponential function, it's impossible to reduce its power, so you're really not making any progress by taking the derivative of this exponential function. This is why you typically want to integrate the exponential function or assign it to be dv, which, by the way, in this case, if I take these two functions as an example and incorporate it here, our u function could be something like the 2x cubed, and then our dv function could be this blob here containing both e to the negative x squared and the differential variable dx. That is essentially how to consider integration by parts notation. Now, as I was saying before, you typically want your u function to be the power function and your dv function to be the exponential function. But let's say that I do have the dv as an exponential function. We have u is equal to 2x cubed. We need to take the derivative of that because we're turning this from u in terms of dv to be vd in terms of du. That means du dx becomes, 6x squared. You move that over there, dx. So then du becomes 6x squared dx. All fine and dandy, sunshine and rainbows, maybe some ramen with a giant egg in it. I don't know. Pick your food. But then we look at the dv function. dv is equal to e to the negative x squared dx. Well, too bad we have no x in front of it. Otherwise, you could use our u substitution. But in this case, since we don't have an x in front of it, well, this integral becomes impossible to solve. Or does it? You see, in this case, with these two functions, you can perform an algebraic manipulation such that you can turn this into a u substitution. Oh my gosh, I can't draw an arrow right now. Let's consider the following. I have 2x cubed multiplied by e to the negative x squared dx. I'm foregoing the bounds right now. I will discuss how to consider an improper integral in just a moment here, after I finish up talking about how to solve this integral. Well, what I was saying before was, why can't we have some sort of x value or x component in front of the e to the negative x squared to turn that into u substitution? Well, you can. And that comes out of the power function. You can represent this as the integral of 2x squared multiplied by x, multiplied by e to the negative x squared dx. And instead of associating the x value here with the 2x squared, you associate it with the e to the negative x squared. That forms, again, your two functions here. This would be u, and now this entire block here would be dv. And as you can see, the integration becomes possible. But before we go on and integrate and solve this problem, let's discuss how to solve an improper integral, right? So an improper integral is very simple. The idea is just that if you have some bound here represented by infinity or a non-finite number, you obviously cannot have an upper bound or a lower bound of infinity since it's not a finite quantity. What you can do instead is you can replace the integral or the integral bounds with a limit of an arbitrary variable that represents going to infinity, and then you replace that bound with the arbitrary variable. Now, for the purposes of solving this problem and keeping space compact, I'm not going to include the bounds as I solve this problem. I will only have the indefinite integral sign there, and then at the very end, I'll reincorporate the bounds to evaluate the integral fully. With that being said then, let us start solving this integral. As we stated before, this function, 2x squared, is our u function, and this function here, x times e to the negative x squared dx, becomes our dv function. So let's write that out here. U is equal to 2x squared, and then dv would be equal to, dv would be equal to x times e to the negative x squared dx. Well, as stated before, we take the derivative of u, du dx becomes 4x. Du, isolate that because we need to sub this du back into here. Du becomes 4x dx. Now in the case of the dv, let's perform the u substitution. Because u has already been taken, I'm going to use a different variable here. I'll call it g. So this is more of a g substitution instead. G in this case would be equal to this exponent here, negative x squared. dg dx would be equal to negative 2x. And then we need to solve for dx here so we can sub it back into here. That's pretty simple though. That would become dx over dg becomes 1 over 2x. You can flip pretty much the numerator and denominators around. Then this becomes dx is equal to negative dg over 2x. Then, plugging everything in, dv would become x over negative 2x multiplied by e to the g dg. But obviously these x's cancel. This becomes negative 1/2 e to the g dg. From there, the integral becomes pretty simple. The integral of dv and the integral of that blob, v would be equal to negative 1/2 e to the g. And plugging back in g, v would be equal to 1/2 negative 1/2 e to the negative x squared. Okay, now we have evaluated both our du value, our du function, and our v function, which means we can perform the first cycle of integration by parts. uv minus v du. Well, we know that u here is equal to 2x squared, and v is equal to negative 1/2 e to the negative x squared, and then minus the integral, again, foregoing bounds for now to incorporate later, of v du. We know what v is. V is negative 1/2 e to the negative x squared. And then du is 4x dx. Negative x squared e to the negative x squared, and minus the integral of negative 2 to the negative 2x e to the negative x squared dx. And again, we see a u substitution here, but I think this might be our final one. U, in this case, would be equal to negative x squared yet again. Du dx, in this case, is equal to negative 2x. Now we need to solve for dx as per usual. Dx over du is equal to 1 over negative 2x. Dx becomes equal to du over negative 2x. We have negative x squared e to the negative x squared here, minus the integral of negative 2x over negative 2x e to the u du. Obviously, these all go away, so this becomes 1. So that's 1 eu du. And then our final integral here becomes negative x squared e to the negative x squared minus e to the u, just e to the u. So that becomes e to the negative x squared right there. And then you can factor out e to the negative x squared. That becomes negative x squared minus 1. And then multiply that by e to the negative x squared, like so. So that would be our final closed form integral solution. And then from here, we just need to incorporate all the bounds in. So this would just be the difference between 0 and infinity. But as stated before, we can't just... Did I say it before? I think I did. Yes. We cannot just have infinity as our upper bound. We need to instead represent that as some form of limit. So limit as an arbitrary variable a approaches our infinite bound. And then that bound here turns to a. I'm going to bring this down here. I'll highlight the difference, or I'll highlight the evaluation at a in red and the evaluation at 0 in blue. So this would be the limit as a approaches infinity of negative a squared minus 1 e to the negative a squared minus the limit as a approaches infinity of 0 squared negative 0 squared minus 1 multiplied by e to the negative 0 squared. So, as you can probably see here, well, it doesn't matter what's in this blob. What matters is out here, actually. You can rewrite this to become the limit as a approaches infinity of negative a squared minus 1 over e to the a squared. This denominator approaches 0 at a very, you could even say an exponentially fast rate. So if the denominator nearly approaches infinity faster than the numerator does, that means that this term here goes to 0. Now, what can we say about this term then? The limit as a approaches infinity of negative 1 multiplied by e to the 0, that would be negative 1 multiplied by 1, and that would be negative 1 in the blue, and 0 minus negative 1 would just be equal to 1. That represents our solution to this problem. Is that an answer choice here? That is, in fact, answer choice B. Welcome and welcome back, everybody. Thanks for joining me as we cover question 15 here. Compute the integral from 0 to pi over 2 of sine to the 5th x dx. So, off the bat, we should look at this 5th power here. This is pretty out of place, and our goal should be to try to reduce this down to a product of terms who have a power of maximum 2. The reason for this is because most of our trigonometric identities, like sine squared x plus cosine squared x equals 1, or tan squared x plus 1 is equal to secant squared x, you'll notice that they actually have maximum powers of 2. So to have a sine to the 5th x, that does not get us anywhere. So first thing we got to do is split this up into the product of sines that all have a degree of less than or equal to 2. So sine square root of x, sine square root of x, like so, dx. And while this doesn't really get us anywhere, maybe we can consider using a trigonometric identity here. The one that I'm looking at is taking this one right here. we can solve for sine squared of x in terms of 1 and cosine squared of x, and then we can plug that back in. We get 0 to pi over 2 of sine of x multiplied by 1 minus cosine squared of x times 1 minus cosine squared of x dx, and that turns into 0 to pi over 2 of sine of x multiplied by 1 minus cosine squared of x squared dx, and a u sub pops out. So the u sub in this case is, this would be our u function. U is equal to 1. Actually, be very careful about this u sub. U in this case should only be equal to cosine of x, because taking like any other thing like cosine squared of x or 1 minus cosine squared of x, that does not result in a derivative of sine of x. Only cosine of x does. So u is equal to cosine of x in this case. Of course, the u substitution is just du over dx is equal to negative sine of x. We need to solve for dx. That's dx is equal to du over negative sine of x, like so. And then we pop the dx back into the thing in terms of du and sine of x. But before we do that, let's evaluate the bounds now in terms of u. And that's pretty simple here. Originally, our bounds are outputs y in terms of x, or they're bounds in terms of x, but to convert them into terms of u, we simply plug them into our function of u here and solve for u at each of those points. So the first one is we have cosine of 0, that's just 1. Then we have cosine of pi over 2, that's just 0. So we have the integral from 1 to 0 of sine of x multiplied by 1 minus u squared, and then dx in this case is subbed in for u over negative sine of x, like so. That cancels, and we're left with the integral from 0 to 1 of negative 1 minus u squared du. Okay, but the nice thing that we can do is we can recognize that, let's just flip this around. The integral from b to a of a function is equal to negative the integral from a to b of that same function, because it's the same area, but you're just integrating backwards. So we're going to flip this. This becomes 0 to 1 of 1 minus u squared du, and this negative sign disappears. So this just becomes a matter of expanding and then integrating with the power rule. So we have 1, what is this? 1 minus u squared multiplied by 1 minus u squared du. This turns into the integral from 0 to 1 of 1 minus 2u squared plus u to the 4th du. This would become u minus 2/3 u cubed plus u fifth over 5 between 0 and 1. That becomes 1 minus 2/3 times 1 plus 1 to the power of 5 over 5. And then everything else in the 0 term becomes 0. So we're left with 1 minus 2/3 plus 1/5. Well, common denominator here, this would become 15 over 15 minus 10 over 15 plus 3 over 15. That would be equal to 8 over 15. And that would be your final answer. That is answer choice A. Welcome back, everybody. Thanks for joining me today as we cover question 16 of this problem set. Compute the integral from 0 to power 4 of tan of x times secant cubed of x dx. With the amount of trigonometric functions that we're seeing on this test, something tells me that these test makers and these test coordinators might have a few tricks up their sleeve. With that being said, let us begin solving this integral. So, right off the bat, I've already underlined this, go me, that we have some function here secant cubed of x. Now this cubed should stand immediately out to us because a general rule of thumb is that we never want to have any function. Is my volume at max? It should be. We never want to have any function or any trigonometric function whose exponent is greater than 2. And the reason for that is because most of the trigonometric entities that we have like sine of square root of x plus cosine square root of x is equal to 1, or tangent square root of x plus 1 is equal to secant square root of x. Or even the power reduction formula, where cosine square root of x is equal to 1 plus cosine of 2 of x over 2. You can notice that all these trigonometric identities have a maximum exponent of 2. In fact, none of them actually have an exponent of greater than 2. Which is why this exponent of 3 should stand out to us here, that this should be our first step in solving this integral. We can reduce it to be a product of 1 secant of x and 1 secant squared of x. Let's do that right now. The integral from 0 to pi over 4 of tan of x multiplied by secant of x multiplied by secant squared of x dx. And actually, we can pretty much stop right here. We're done. So, here we spot a nice u sub. The u sub in this case would be that the u function is equal to secant of x, and our du dx function would be this thing right here. That's all to say. Remember, u is equal to secant of x. Du dx is equal to secant of x, tan of x. We must solve for dx as we plug it back in to the original function for a proper change of base. Dx over du was equal to 1 over secant of x, tan of x, which means that dx is equal to du over secant of x, tan of x. I'm going to skip all the canceling work here. If you just plug back in dx into the original function and replace it with du, you'll find that everything cancels out nicely. So the next step to do is we need to evaluate the bounds to be in terms of u, the function u instead. Now this is pretty simple. We see that u here is in terms of x. We just need to plug in each x value into the function u of x, which in this case is just secant of x, and then evaluate the corresponding u outputs. So for example, u of 0 would be equal to secant of 0, which is equal to 1 over cosine of 0, which is just 1. Therefore, u of 0 is 1. That would be our lower bound. And then u of pi over 4 would be equal to secant of pi over 4, which is equal to 1 over cosine of pi over 4, which is equal to 1 over root 2 over 2. That would be equal to 2 over root 2, which would be equal to root 2. With that, we can now begin solving this integral. We have found both bounds. That'd be from 0, that'd be from 1 all the way up until root 2 of u squared du. Actually, as you'll notice, I have skipped the canceling part, but just trust me on here to say that once you plug back in dx, secant x, tan of x cancels, and you're left with u squared du, where u is equal to secant of x. This is a simple power rule integration from u cubed over 3 from 1 to root 2. Now this is just simple bounds. This will become 4, this will become root 2 cubed over 3 minus 1 over 3. That become 2 times root 2 over 3 minus 1 over 3. You could represent this as 2 root 2 minus 1, all of that over 3, and that perfectly matches answer C, which would be the answer to this problem. Welcome and welcome back, everybody. Thanks for joining me today as I cover question 17. The appropriate trigonometric substitution will convert the following integral, shown below, into one of the 5 answer choices. Right off the bat, we know that if we're looking for a trigonometric substitution, we must look for a trigonometric identity. That is our most important step. But what we should consider when looking for this trigonometric identity is that once we make the basis, or the change in basis from x to theta, our polynomial turns into a function that contains secant and tangent, or maybe even a product of the two of theta. Which means that our trigonometric identity must contain only and both tangent and or secant of theta. There's really only one trigonometric identity that does that. Tangent squared of theta plus 1 is equal to secant squared of theta. Or more generally, if you have a coefficient of c attached to that, c tangent squared of theta plus c is equal to c secant squared of theta. Now this becomes pretty important in just a moment. Let's begin solving this problem then. What we need to do is we need to somehow turn this polynomial in a standard form into a form that can be rewritten as some function squared. In this case, it's just tangent, but this function could be replaced by any function, u squared, plus 1, or plus some constant out in front, we'll call that a, is equal to a secondary function, g squared. But we're mostly focused on this first part of the expression. And there's one way to do that, and that would be through completing the square of the polynomial. That's just to say that if I have some polynomial in a standard form, we'll use this as an example, x squared minus 4x plus 29, I can represent that as both the product of a perfect square polynomial. In this case, it would be x minus 2 squared, and I'll show why, or show how to see that in just a moment, and then plus an additional constant d to sort of rebalance everything. So let's take this polynomial, for example, to show why it might be x minus 2. Well, if I have x minus 2 squared, just on its own right now, I expand that out, that becomes x minus 4x, x squared minus 4x, and then plus 4. You'll notice that the b coefficient is just double what's inside of here. Same goes for something like x minus 6 squared. X squared minus 12x plus 36. You'll notice again, negative 12 is double that of negative 6. So it should follow then that if we have a b value of negative 4, then what is inside our perfect square polynomial should be negative 2. And the reason why we need a d out in front is because if we're saying that x squared minus 4x plus 29 is equal to x minus 2 squared and then plus some constant d out in front, well, let's expand that out. X squared minus 4x plus 4 plus d is equal to x squared minus 4x plus 29. Well, obviously these all cancel out, so we don't need to worry about them. We're left with 29 is equal to 4 plus d. Now let's say we did not have the d out in front. Well, it doesn't take someone with a quarter of a brain to notice that 29 might not actually be equal to 4, right? Or maybe if you have like an eighth of a brain, maybe you can't recognize that. I don't know. I'm hoping that nobody here doing engineering school has an eighth of a brain left in their head. If so, you might need to change majors. But as you'll notice then, we need to have some additional constant out in front. I'll represent that as d in order for this equation to even be possible. Now in this case, d is very clearly equal to 25, which means that if we were to represent this in a completed square format, that would become x minus 2 quantity squared and then plus 25 out in front. And as you'll notice, we've actually perfectly established that we've reached a format that can be represented as a function u squared and then plus some constant out in front, which is a. But we should notice then that this format here, actually this should be u squared plus 1. We notice then that this term here is not 1, it's 25 actually. So then how do we account for that? Well, we look back to the trigonometric identity, the more general solution that I've established below, where c tangent squared of theta plus c is equal to c secant squared of theta. Well, if we're to write this out in terms of c tangent squared of theta, and then plus 25, you might notice then that c here has to be equal to 25 for our trigonometric identity condition here to work. So c must be equal to 25 for the trigonometric substitution to work. We can rewrite that out to be like this. X minus 2 quantity squared, then plus 25 is equal to 25 tangent squared of theta, and then plus 25, right? And then now we can pretty much perform the trigonometric substitution. Almost. What we need to consider before that, though, is we're making the change of basis from x to theta, right? So we need to find how x might be in terms of theta. Now that's pretty simple. We can cancel out the constants here. We're left with x minus 2 squared is equal to 25 tangent squared of theta. You can take the square root of both sides. You get that x minus 2 is equal to 5 tangent squared of theta. Now you'll notice I've only taken the positive roots, even though it is possible for you to take the negative root. However, doing so will introduce unnecessary signage, unnecessary negative signs that I want to avoid by just taking the positive root instead. So x minus 2 is equal to 5 tangent of theta, my mistake. Then that means that x must be equal to 5 tangent of theta, and then plus 2. Now, that's not going to be really important for actually substituting in. This is more important for locating the bounds and then also making the formal change from dx into d theta, as we'll see in just a moment. So I'm going to split this up into two processes here. I'm going to split this up into finding bounds, if I can write, and change variable. So changing variable is just like how we do u substitution. This will literally just be dx d theta is equal to, what is this? 5 secant squared of theta. Well, dx is equal to 5 sec. I keep seeing that as a s. 5 secant squared of theta d theta. We can pretty much just sub that directly in, right? Now I got to find the bounds, because as we make a change from x into theta, then our bounds must change to be from in terms of x to be in terms of theta instead. That's pretty simple though. As I usually do for u substitution, we simply plug in values of x, and then we solve for theta. The first x value that we have is 2 is equal to 5 tangent of theta plus 2. Well, then 0 is equal to 5 tangent of theta. Tangent of theta is equal to 0. That would just be when theta is equal to 0. So that would be our lower bound. Now our upper bound is a little different. 7 is equal to 5 tangent of theta plus 2. Oh, well, I can move the 2 over to the other side. 5 is equal to 5 tangent of theta. That means that 1 is equal to tangent of theta. Now there's only one case when tangent of theta can equal 1. If you remember that tangent of theta is equal to sine theta over cosine theta, that means that sine theta and cosine theta must be equal at the point when tangent of theta is equal to 1. This can only happen when theta is 45 degrees, or when theta, represented in radians, I keep doing this stupid thing, is equal to theta would be pi over 4. That would be your upper bound of theta, since this value of theta is associated with 7. So with that being found, then, we can begin setting up the integral for this problem. Thank the gods that we do not have to actually solve it. We see the integral from 0 to pi over 4 of the square root all of that. But we saw before then that this polynomial here, boxed in red, I'm going to take out this blue x here, is equal to this trigonometric representation shown in blue, but this polynomial shown in red is equal to the standard form shown above, which means that we can directly substitute in 25 tangent squared of theta plus 25. That becomes 25 tangent squared of theta plus 25, all of that under the square root, and then we need to substitute dx in for whatever it's equal to in terms of theta. That would become multiplied by d theta, multiplied by 5 secant squared of theta, d theta. As you may notice, though, we can factor out a factor of 25, which means it becomes 25 multiplied by quantity 25 multiplied by tangent squared of theta plus 1, all of that in parentheses. And then multiply that again by secant squared of 5 secant squared of theta, d theta. Recall then, though, that the identity tangent squared of theta plus 1 is equal to secant squared of theta, which means you can sub in secant squared of theta. Then we get 0 to pi over 4 of the square root of 25 secant squared of theta is multiplied by 5 secant squared of theta, d theta. You take the square root of everything, you get the integral from 0 to pi over 4 of 5 multiplied by secant cubed of theta, d theta. This will just become 25. And this is the most simplified version of our integral. Is it equal to the answer choice? That would in fact be equal to the answer choice A. Hello everybody, thanks for joining me today as we cover question 18. Evaluate the following integral. So, what we can notice here is that we have a square root, which means that partial fractional decomposition is off the list. We have no possibility of u sub in this case. That's pretty evident. But what we can notice is that we have a polynomial sitting inside of the denominator, sitting inside of the square root. So maybe we can try, as we know, polynomials can be rewritten or represented in terms of their vertex form, which can be written as a trigonometric identity. So maybe what in this case we need to do is use a trigonometric substitution to change the basis and then solve the problem in terms of theta. Right off the bat though, we should notice that the x squared term is actually negative here. So we have two possibilities of trigonometric identities. We either have that tan squared of theta plus 1 could be equal to secant squared of theta, or we have some form of sine squared of theta plus cosine squared of theta is equal to 1. But we have no idea about which to use until we start working this out. Obviously, we know in order to do a trigonometric substitution using a polynomial, we must turn this into its vertex form, and to do that, we must do something called completing the square. This is more detailedly covered in a previous one. This is better covered in question 17. But for the purposes of this problem, I'm going to go right ahead and begin solving it. So completing the square, we have negative x squared plus 8x minus 7. For the purposes of making this a little bit easier on my brain, I'm going to pull out the negative sign. So it becomes negative, in parentheses, x squared minus 8x and then plus 7. This becomes pretty easily factorable. Not factorable, actually. We're not hoping to factor this. This becomes negative, and then x minus 4, x squared, and then minus 9 out in front. Now we can pull the negative sign back out, or redistribute it, we get 9 minus x minus 4 squared. That would be what we can represent this polynomial as instead, in terms of its vertex form. Now you may be thinking, okay, that immediately crosses off this off the list, but this, we might be able to use some form of sine squared of theta plus cosine squared of theta is equal to 1, and that becomes more evident if we move one of these over. So I'm going to move over for these purposes the cosine squared of theta. That means that sine squared of theta on its own would be equal to 1 minus cosine squared of theta. And that pretty nicely matches the form that we have here. But what we have is a 9 compared to a 1. Well, what do we do then? We know that if this value in this trigonometric identity is 9, that means that the coefficient in front of the cosine squared of theta must also be 9, right? If that's the case, then that means that x minus 4 squared here must be equal to 9 cosine squared of theta. Now, remember that in order to make the trigonometric substitution, we need to figure out how to represent the function or the variable x to be in terms of theta, right? So we're going to split everything up into two processes here. The first is we need to change base, change variables. To do that, we obviously need to figure out how to represent x to be in terms of theta. That's pretty simple though. That becomes x minus 4. You take the square root of both sides. That becomes x minus 4 is equal to 3 cosine of theta. X is equal to 3 cosine of theta plus 4. You take the derivative, you get x is equal to negative 3 sine theta plus, negative 3 sine theta. Dx d theta is equal to negative 3 sine theta. And then you move d theta over to the other side, you get dx equals to negative 3 sine theta d theta. That finds the dx differential, which you can sub right back into the original equation. Then we need to find the bounds. Because as we know, once we change the our variable basis, we are also changing the bounds to be in terms of originally from x to now be in terms of theta. That's pretty simple though. We have already found our x function here. X is equal to 3 cosine theta plus 4. All we need to do now is we need to plug in the values of x at each of these bounds and then solve for the corresponding theta values. So first we have for the lower bound we have 4 is equal to 3 cosine of theta. plus 4, well, cosine of theta must be equal to 0. Theta then must be equal to pi over 2, because it's the first possible theta value that produces a cosine value of 0. The second one is 11 halves. 11 over 2 is equal to 3 cosine of theta plus 4. This turns into 3 halves is equal to 3 cosine of theta. That means that cosine of theta must be equal to 1 half, which means that the theta upper bound must be equal to, what is that? Pi over 3? Right. Perfect. So that means we found both of our theta bounds here. Our theta lower is equal to pi over 2. Our theta upper is equal to pi over 3. And now we can begin setting up the integral. So as we've established before, this entire thing, 9 minus in parentheses x minus 4 squared, is just equal to negative x squared plus 8x minus 7. So if we replace the x minus 4 squared with the 9 cosine theta, this becomes 9 minus 9 cosine squared of theta, which we can directly sub in to its original spot. This integral becomes the integral from pi over 2 to pi over 3 of 1 over the square root of 9 minus 9 cosine squared of theta d theta. Oh, not d theta. It would be negative 3 sine theta d theta. From there, what we can see is we can factor out a 9 from this thing. We get the integral from pi to over 2 to pi over 3 of negative 3 sine theta over the square root of 9 times 1 minus cosine squared of theta d theta. Well, this is pretty evidently just sine squared of theta, like so. We have the integral from pi over 2 to pi over 3 of negative 3 sine theta over, pull out the 9 from the square root, that becomes 3, pull out the sine squared of theta, that becomes sine theta d theta, which means that the integral just turns into pi over 2 to pi over 3 of negative 1 d theta. That is just negative theta from pi over 2 to pi over 3. That would be, that would be negative pi over 3 and then plus pi over 2. That would be negative 3 pi, negative 2 pi over 6 plus 3 pi over 6. That would in fact be pi over 6, which corresponds with answer choice C. Hello everybody. Thanks for joining me today as I cover question 19 of this problem set. Which of the following series converges absolutely? Let's quickly take a second to define what absolute convergence means. If a series converges absolutely, that means for alternating series like all the ones that are shown in this problem, if they weren't alternating and they weren't converging to one point, if we just considered the magnitudes of each of the values in the series, or the absolute values of each of these values in the series, and then we sum those magnitudes together, would the series still converge? Would the sum still be finite? That is what we're here today to figure out. So let's look at the first example then. If we're taking the absolute value of this, that means that the negative 1 to the k goes away. It just becomes a series from k equals 2 to infinity of 1 over root 3 of k cubed plus k. Now, we can probably tell that we need to use a p-series test to evaluate this, but we have this pesky k to the first power sitting behind this much bigger k cubed. Let's consider this at a very, very, very large value near infinity. If we have 1 over to the root 3 to the third root of k cubed plus k, where k is a ginormous number, well then k cubed is much, 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 much bigger than k at that point. So much that this k cubed plus k can pretty much be approximated as k cubed. So at very large values then, this first series, or the terms in this first series, become a form 1 over k to the first. This means that this first series does not converge absolutely. It actually diverges, only considering its magnitude values, because it fails the p-series test, since the exponent in the denominator is less than 2. right off the bat, we can say, A, you are not our answer choice, which is very, very sad because A is my first initial of my first name, but alas, not everything can be given to me. Let's look at option B. This becomes, or actually, I think it's better to do it down here. I'm actually going to do it down here. This becomes 1 over k cubed plus k. So it's a similar scenario of a p-series. We no longer have the square root sitting out in front. We'll try the same thing again. If we plug in a huge value for k, we find, again, that k cubed is much, 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 much larger than k, which means that this can pretty much be approximated to just 1 over k cubed. This does, in fact, pass the p-series test. But, just to make sure that we're not shutting out all of our other answers, let's keep this one on the boilerplate for now. This one might be correct, which is why I highlighted in green. Let's look at the third one. The third one is the root to the kth root of 1 over k to the fifth. Well, pretty evidently, once k becomes greater than 5, this series turns into, well, this series has always just been 1 over kth root of k to the fifth, but once k becomes greater than 5, all the subsequent terms become a form k over 5 to the k, where k is greater than 5. That means that the exponent is guaranteed to be less than 2. Well, actually, it's guaranteed to be less than 1, right? Which means that it fails the p-series test. That means that C is no longer an option. Let's look at D now. Oh, sorry. Let's look at D. D is a series of 1 over ln of k. And we can do a comparison test here of two functions. So we have our first function here is equal to ln, or f of k is equal to ln of k. And we can compare that to another function we'll call g of k is equal to the square root of k. And we know that the square root of k, or you probably should know that the square root of k is larger than the natural log of k for all values of k. So we're comparing the series of 1 over ln of k and the series of 1 over the square root of k. Well, we know that if ln of k is less than the square root of k for all values of k, that means that the terms in this series must be greater than the terms in this series. But we already know that this can be represented as a series of 1 over k to the 1/2. And this specific series fails the p-series test, which means that this series diverges. But if this series diverges and its terms are smaller than the terms here, that means that this series ln of k has to diverge as well, because it's guaranteed to produce a larger sum than a diverging series. Which means that answer choice D is incorrect as well. Okay, our last choice here we have now is E. This can be represented as the series of 7 over k squared, or 7 to the k over k squared. Our best option here is to use the ratio test. So the ratio test just says that if I have one term that is one index or one input of k greater than the previous term, and I take the ratio of those two, I can determine whether or not the series grows or whether or not the series diverges or converges based on the ratio that I get between these two consecutive terms. So I have the absolute value of 7k plus 1 over k plus 1 squared, and that is over 7k over k squared. So let's look at this. This will become the absolute value of 7k times 7 over k plus 1 squared multiplied by k squared over 7k. That cancels. And we're left with 7 multiplied by k squared over k plus 1 squared. Well, as k approaches infinity, as we see in the series, well, this specific quotient here approaches 1. It does not approach any other value besides 1 because eventually, as k gets huge, well, this denominator just goes to k squared, so you end up having 7 times k squared over k squared at very large values of k, which means that the ratio test for answer choice E would represent in a ratio of 7, which means that obviously the series must diverge because each term is getting larger and larger and larger as k increases. So we know that E must be wrong. That confirms that B is the correct answer choice to this solution. Hello everybody, thanks for joining me today as I cover question 20. Find the interval of convergence for the power series shown below. Okay, if you can hear talking in the background, I apologize, I'm in a public space. As quiet as it can get it. So the interval of convergence for this power series here. Now, right off the bat, we should talk about what the interval of convergence is actually looking for. This, I'll identify as IOC, is dependent on a convergence test called the ratio test. The ratio test essentially finds the ratio between two consecutive terms, a sub k plus 1 and just a sub k. If the magnitude of the ratio is less than 1 for all terms of k, so we apply a limit here, then that means that the series must converge. The reason why we need the limit as k approaches infinity here is because that guarantees that there's no asymptote or there's no region where the terms are essentially all equal to each other. So I can give an example of where this might be the case. If we have the harmonic series here, the sum of all terms 1 over k, if we graphed out what 1 over k might look like, you'll notice that at some point it actually starts approaching an asymptote. If it approaches an asymptote, then all the terms forward from the beginning of the asymptote, they're practically the same value. That means that the series is infinite because you're adding the same value over and over again. None of the values are actually approaching 0 anymore. That is why the harmonic series diverges. However, in the case of 1 over k squared, if you visualize k squared, you can apply the ratio test to this one actually too. You'll notice the terms die out much faster and continually approach 0 at a much faster rate. In that case, then, you can begin approximating the terms as being equal to 0, which is why the 1 over k squared series converges and produces a finite sum. That is why you need the limit out behind or out in front of everything. Now, in the case of the interval of convergence, we're provided with an additional variable here called x. We need to find all values of x in which this series can converge. So let's apply these two principles here. We need to apply the ratio test as described before, and then we need to solve for a region of x. This region of x that is valid, that produces a valid and converging series, is what we call the interval of convergence. So in this case, we need to find two things. We need to find what is the a to the kth term, which is actually just what is described in here, negative 1 to the k over 4k times k plus 5, multiplied by x minus 3 to the 2k. And now we have, additionally, a to the k, a sub k plus 1, that's the next term. That would be just adding 1 to k in every single instance. So that'd be 4 to the k plus 1 multiplied by k plus 6, then x minus 3 multiplied by 2, and in parentheses here, k plus 1. Do not write that as 2k plus 1 on the test. Obviously, it's k plus 1 because the k is not attached to the 2. So you need to separate the k from the 2, then add the 1. With that being said, then we can do the ratio test. This is limit as k approaches infinity of a sub k plus 1 over a sub k. And as a reminder, we need to evaluate, is this series, does this limit here is this limit less than 1 once finished? So this we can substitute in. This would be negative 1 to the k plus 1 multiplied, or actually divided by 4 to the k plus 1 multiplied by k plus 6 over multiplied by x minus 3 to the 2k plus 1 in parentheses over negative 1 to the k over 4k times k plus 5 multiplied by x minus 3 to the 2k. So, like I said before, we need to preserve the variable x in here, but we can probably evaluate this to some constant multiplied by x. If we expand everything out, we get -1. Actually, well, first of all, these terms become irrelevant because we're taking the absolute value of this. So this is just 1 over 4k, bring out the 4 multiplied by k plus 6, multiplied by x minus 3 to the 2k, multiplied by x minus 3 squared, over 1 over 4k times 4k, k plus 5, multiplied by x minus 3 to the 2k. You can already start to see here, some of these terms die out. The 4k's cancel, these cancel. Now we're left with something that looks like this. The limit as k approaches infinity of x minus 3 squared, this would be divided by k plus 6. Then this goes up into the numerator, multiplied by k plus 5. Now, what we're left with then is x minus 3 squared multiplied by this ratio between these two terms. But if k approaches infinity, then k will become so large that k plus 5 could be pretty much approximated to equal k at such a large value of k. If that's the case, then these two terms become insignificant, and we only look at the ratio between the significant factors of k here, which is k over k. That'd be the limits as k approaches infinity of x minus 3 squared. Oh, sorry, forgive me, the 4 here. Bring out the 4. X minus 3 squared over 4 multiplied by k over k. This reduces to 1. So we're left with this as our final, most simplified version of the expression. This must be less than 1. So we'll do that. As you'll notice, there's no more k instances in this inequality, so we can just eliminate the limit here. And we're left with the absolute value of x minus 3 squared over 4 must be less than 1 for all values of x. But we notice there are no terms in here with a negative value, so we can take that out. So it's x minus 3 over 4 must be less than 1. Well, we need to solve for x. Bring the 4 over. X minus 3 squared must be less than 4 in this case. All right, the next thing we can do is take the square root. But if we're taking the square root, we need to keep in mind that we could possibly branch off into two separate things here. If we take the square root, we get x minus 3 could be less than just 4, but x minus 3 could also be greater than -4. And let's take, for example, what we're seeing here. If you take the square root of this, you take the square root of both sides, this becomes effectively the absolute value of x minus 3, because anything in here must be positive. Anything that comes out of x minus 3 squared must be positive, which means that if you take the square root of that, everything that comes out of x minus 3 must also be positive. And the way that you do that is through the absolute value. This must be greater than 2. All right, that splits off into two inequalities here. X minus 3 must be less than 2, and x minus 3 must be greater than -2. If we define a region here, okay, perfect. So x minus 3 has to be less than 2 in this case. We're moving the absolute value here, so it turns into this, right? So it becomes x minus 3 must be less than 2. The function must be less than 2 here. So all values within this region, moving backwards. But the function must also be greater than -2. So we define the second bound here. So we're only looking within this region of values. That means that x must be less than 5 and x must be greater than -1. Or x must be greater than 1. So we defined this region. 1 is less than x is less than 5, for which all values are guaranteed to result in a convergent series. But we should also check the endpoints here, 1 and 5, and see if at those endpoints, does the series also converge. So I'm going to move back up here. I'm going to erase some previous stuff that I wrote down, and we're going to check that. And we do that by simply plugging in the values of the bounds for x. So take, for example, here, we plug in 1, we get this, the sum of all terms -1 to the k over 4k times k plus 5. That would be 1
minus 3. That'd be negative 2 to the 2k. You could split this up. This would become negative 1 to the k over 4k to times k plus 5 multiplied by negative 2 to the k times negative 2 to the k. This can be brought in. This would be 2 to the k multiplied by negative 2 to the k over 4k multiplied by k plus 5. That would become negative 4 to the k over 4k multiplied by k plus 5. That turns into, what is this? Negative 1 to the k over 1 to the k. Sorry, negative 1 to the k. The reason how I got that is you can turn this into the sum of, let me get this out of here. I don't need the rest of this. This turns into negative 1 over 1, sorry, negative 4 over 4 to the k multiplied by 1 over k plus 5. And of course, that would turn into the sum of negative 1 to the k over k plus 5. Now we can apply the alternating series test to this function, or the series, because it is an alternating series. All terms must approach 0 over very large values of k. It's pretty obvious here that if we have negative 1 on the numerator, negative 1 to the k on the numerator, and an increasing k plus 5 on the denominator, that all terms should probably go to 0 over time. So we know that it converges at 1. Now we need to check for 5. Does it also converge for values at x equals 5? And the way to do that is, again, just plugging in values at 5. This would become positive 2 to the 2k. Again, we can split this up. Negative 1 to the k multiplied by 2k multiplied by 2k. That would be, actually, this could probably be written as 4 to the k. We'll do that right now. So k plus 5 like this. Then we have negative 4k multiplied by k plus 5 here. I just realized that you can bind these into 4k. So we have negative 1, I'll write it back in black, negative 1 to the k multiplied by 4k over 4k times k plus 5. These cancel. We're left with, again, the series of negative 1 to the k over k plus 5. As you can see here, this is the exact same series as before. All terms here go to 0, and the series is an alternating series. That means it also converges at x equals 5 because it satisfies the conditions of the alternating series convergence test, which means that C must be our answer choice for this problem because it contains both 1 and 5 in their interval of convergence as signified by the brackets on both sides. Hello everybody, thanks for joining me today as we cover question 21. Compute the value of the series. The series is shown below. We are given 3 hints. Firstly, we can observe that this series here, originally given in the problem, can be rewritten as form of the initial term in the numerator multiplied by some arbitrary term, x to the k, which can then be factored into k plus 2 times k plus 1 times x to the k. And we're also given this function here can represent the power series where a equals 1. That is represented as the sum of all terms from k equals 0 to infinity of x to the k power, which is equal to 1 plus x squared, blah, 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 going forward. We're asked to compute the power series for f prime, double prime of x. And then we can make an index change here in some capacity for k to turn it into some different variable. How does the power series for k f of double prime of x compare with the one that's shown in 1, which is this one right here? And then apparently, using this information, we can find the value of the original series. So right off the bat, we can take the original series here, we can take this relationship and perhaps solve for the value of x. And in this case, it should be pretty simple what x should be if we have k squared plus 3k plus 2 over 3k. We can set that equal to k squared plus 3k plus 2 for some value. I wrote the answer out, but it should be conceptually x to the k.
Now, okay, these terms should go away. So this should go away, that should go away. Mathematically solving for it, we get 1 over 3k should be equal to x to the k. It's pretty obvious then that x should be equal to 1/3. That solves for us one of the components that we need for this series. Now, of course, the second one we need to know is what should be a. That is not entirely relevant just yet, actually. We don't need to know what a is. Well, what we need to start looking at is this power series here. F of x is equal to 1. Actually, it can be rewritten as 1 minus x to the negative 1 power. If we differentiate that twice, we get f prime of x equal to negative 1 multiplied by 1 minus x to the negative 2. Of course, following the power rule. Then do it again. F double prime of x is equal to 2 times 1 minus x to the negative 3 power. That is equal to 2 over 1 minus x to the cubed, or x cubed. Okay, now literally writing out, we can also look at how this series, or its series format, is differentiated here. So we have, of course, f of x is also equal to the sum of all terms x to the k from k equals 0 to infinity. If we take the first derivative, that becomes the sum of all terms. Not going to write that out again. That'd be k multiplied by k, x to the k minus 1. Then f double prime of x is equal to the sum of k times k minus 1 multiplied by x to the k minus 2. Now notice something here. This term is k. That term is 1 less than k. This term can be represented as j. And this term is represented as 1 less than j. So these terms can be considered as kind of equivalent. Actually, they might be exactly equivalent. Let's see here. We'll write this, we have k here represented as k, but then we have the alternative series here represented as the sum of everything from j multiplied by j minus 1, where j is equal to k plus 2. That means that also then the j minus 2 would be equal to k, right? This is important because we can make a substitution right here. We can rewrite this as x to the j minus 2, subbing that in for what we found for k. That'd be x to the j minus 2. And as you can see here, these two series are perfectly similar to each other, which means that solving for the value of this series will solve for the value of the original series, k squared plus 3k plus 2 over 3 to the k. That also means then that this value of x equals 1/3 can be subbed in for whatever value of x we see here in this function, 2 over 1 minus x quantity cubed. The relation then we can say is that f double prime of 1/3, that would be equal to 2 minus 1 minus 1/3 cubed. That should in fact be equal to the original series of sum of k squared plus 3k plus 2 over 3 to the k. So we just need to evaluate this now. I'm going to bring this over to the left side here. Oh, I can draw that better. Right here. That would become 2 times 1 over 2/3 cubed. That's equal to 2 times 3 over 2 cubed. That'd be equal to 2 times 27 over 8, which is 27 over 4th. That would be our final answer to this problem. That would in fact be answer B. Welcome and welcome back, everybody. Thanks for joining me today to cover question 22. As you'll notice, I've changed scenery. No longer am I in the original PDF. I am now in Microsoft Whiteboard. That is because this problem takes a hell of a lot of space and a hell of a lot of math. And to put this amount of space on the paper that you will use to evaluate everything is kind of criminal. And I feel bad for you guys. With that being said, though, let's get right into solving this problem. Choose the right formulas to compute the volume of the solid obtained from rotating about the line x equals 3, the region is given below, using both the washer method and the shell method. The region is bounded by a downward spacing parabola, a vertical line, and a horizontal line. So
before we do anything, let's begin by identifying the region. There's only really one region that's bounded by all three curves, and that would be this dinky looking thing right in the middle of the page. It would be this shape right here. With that being said then, let's begin by looking at how we would evaluate this using the washers method. So I'm going to do it off to the right, appropriately titled washers, like so. I'm going to take the shape that we have directly. The shape would look something like this, and our shape is revolved about a vertical axis and not a horizontal axis. That does in fact change a few things when we evaluate our washers method. Most importantly though, is the orientation of the washers. Should the shape be rotated about the x-axis like it would be in this scenario, your washers would be vertical like so. But you obviously cannot have vertical washers if your body is rotated around a vertical axis. That is where we employ the shell methods. To calculate this through the washers method, let me draw out the vertical axis of rotation here. That's our axis of revolution. Our washers are now horizontal. What we can do is you can take this shape and you can divide it into an infinite amount of very, very thin discs with holes in them. So for example, this disc right here, this would be one disc. This disc has a very, very small thickness dy. That would be the outer radius of the disc, or the outer diameter of the disc. And then the inner diameter of the disc represents the area that has been consumed by the hole. We can draw this shape out and it would look something like that. It would look something like this. That would be the shape, and then plus a little bit of thickness here. As it turns out, you can evaluate this shape as a sum of both the outer cylinder's volume minus the inner cylinder's volume that represents the hole within this washer shape here. And that will give you that. That means we need to define a few things here. First of all, we need to find the function of radius of the outer circles. We'll call the radius of the outer circles r big. And we need to find the radius of the inner circles that represent the holes. We'll call that r small. Now, in this case, that will be pretty simple. However, we need to establish one thing, and this applies for every single thing, or every single calculation that we do with these volume of solids revolutions problems, and that's your coordinate system does not change depending on where your axis of revolution is. If your axis of revolution is not along the x or y axis, that does not mean that you still go outwards from the axis of revolution. No, you always calculate as if you're starting from the origin and you're moving upward or you're moving rightward. For example then, that means to find the radius of the big washer, that would be from the axis of revolution to our function of parabola here, this one, right there. I'm actually going to cut off this side right now to better represent them as radius, but it will look like that, right? You do not immediately find this distance. What you do instead is you find the total distance from the origin axis, that would be x equals 0, to the axis of revolution, s equals 3. That total distance will represent as a capital. That will be d is equal to 3. Then we need to find the distance here. And then by finding this distance right there, we can subtract this smaller distance, d, from this larger distance, capital D, to find our radius function for the outer. D here would just be equal to the function's output as the function moves upwards with respect to y. That means we need to take the original function that we have here, which is y equals negative x squared plus 4, and put it to be a function y, put it as a function x in terms of y. That's very simple. We simply do y minus 4 equals negative x squared, move the 4 to the left side, then put the sign out to the left side, then take the square roots, 4 minus y is equal to x. Now, you'll notice there would be a plus minus here, but since we're only considering the positive region and not the negative region that look like this, we can disregard that signage and we can only take into account the positive side of this square root function. So, this distance d here that I've drawn out, that would actually just be equal to the function 4 minus y. But that's not what we're after. We are after this distance here,
that would be considered the r big in this case. Well, r big is just equal to the large distance minus the small distance, which is d, capital D, minus small d. That would be 3 minus the square root of 4 minus y. That would find our bigger radius to use to calculate the washer's area and volume. Now we need to find the small radius. The small radius is a little bit easier. That would simply be from this vertical line to our axis of revolution. This vertical line here is defined as x equals 2, and our axis of revolution is defined as x equals 3. That means the radius of the bigger function, or the radius of the smaller radius function would just be r small. R small would just be equal to 3, or absolute value, 2 minus 3. That would be equal to 1. I have the absolute value there because you can't have a negative radius. That means that we found both of our radii functions here. Now we're pretty much ready to solve for, we're ready to set up our integral. But keep in mind though, one more thing. This has a very small thickness of dy. That is how we obtain our volume. That means that the volume of one of these shells, so let's say one of these washers, washer individual, that would be pi times r big squared minus pi times r small squared, and then multiply that by dy. Because this is the area of the larger circle, area of the smaller circle, then you're applying a thickness to that washer shape. All right, the last thing we need to do is we need to find the bounds. Now, if we look back at our shape here, I'm going to draw it on here for simplicity, or because it's cleaner. We're moving in the y direction because our integral is with respect to dy. That means then that our bounds, the shape of our bounds, should look like horizontal lines instead, because that's where we can guarantee that we cut off our integral at. So the only two horizontal lines that I see that define the upper and lower bounds of the region are the x-axis at y equals 0 and this line here, y equals 4. So these two would be our upper and lower bounds of integration, and with that we can finally set up our integral. Our total volume is the integral from 0 to 4 of each of these small little volumes here. That would be pi multiplied by the bigger radius squared is 3 minus the square root of 4 minus y squared, and then subtract that from the smaller area, pi times 1 squared, and then give that little bit of thickness dy. That would be the volume done by the washer's method. Let's look at how to do it with shells. So shells would be this. It's sort of the same principle, but it's like if you were doing vertical washers instead of horizontal washers. Let's say I still have my shape here. My shape looks like this. I draw out my shape kind of like that. My axis of revolution, obviously. If I were to do vertical washers, that wouldn't exactly be possible. What I can do instead is I can do spherical shells or cylindrical shells. If I draw out my shape in 3D, my shape kind of looks something like this. Right? I can define spherical shells that radiate outward from my axis of revolution. Now, these spherical shells, you might notice, they have a total height of the upper function. We can define an upper height function. I'll call that f upper or fu. Laugh at that if you like. And then subtract that from a lower height function, which would be, in this case, this would be fu from the origin axis to that function, and subtract that from a lower height function, fl. And subtracting fl from fu would give the total height of each cylinder. So the height here would be equal to fu minus fl. We notice that the radius here, we'll define in a second. I'll just do that as r. And each of these shells have a very small thickness of dx. Okay, let's look at first how to evaluate the height function. Well, if we look back at the image here, or our little graphic, we notice this horizontal line is actually our upper height function. That is y equals 4. So we can define our fu function as a function of x to just be the value of 4. Now we need to look at what fl might be. Fl, the lower height function, would be the distance from the x-axis up to the downward-facing parabola.
that would just be f L of x is equal to negative x squared and then plus 4. So really what you're doing is you're taking this height from 0 all the way up to y equals 4, and you're subtracting it from 0 to y equals negative x squared plus 4. And that gives you this height in between for each of these shells. All right, now let's try to evaluate the function of radius here. And we use the same principle as we did when evaluating something back there. I'll just show you here. Our radius extends from the axis of rotation outwards to a point x here. But of course, as I described before, you cannot think about it as literally, or you cannot calculate it as if you're starting from the axis of revolution and you're moving outward. You always need to define all your points from the origin axis and then move outwards from the origin axis instead. That means in the same way, I would define a total distance here. That would be d. That would still be 3. And then I have a smaller distance here. Let's say that I traveled the distance from the origin to a distance x0 along the x-axis. Well then, that means I could define this part of the distance to be my radius. That means the radius here would be equal to the total distance, which is 3, minus the distance that I traveled from the origin, which is x, or x naught. So that'd be 3 minus x naught. But if I wanted to make it as a function of x and generalize my radius, I can rewrite that as just r equals r of x is equal to 3 minus x. And that means that I found my function of radius as I travel a distance x from the origin. Which means then that we found everything we need to evaluate this cylindrical shell. Let's consider what the formula might look like. I have my cylindrical shell here. It has a height of h, it has a radius of r of x, and it has a small thickness d of dx. I can lay this cylindrical shell out as kind of like a rectangular prism, because at the end of the day, a cylindrical shell is just like a rectangular prism. You've just kind of rolled it up. It's like taking a paper and then rolling it up into it's like taking a paper and rolling it up. Same principle. It still has a thickness of dx, has now a width of 2 pi and then multiplied by the radius function, and still has a height of h. This small volume of this shell would be equal to length times width times height, which is just 2 pi r of x multiplied by h multiplied by d of x. We already know what r of x is. That'd be 2 pi multiplied by 3 minus x multiplied by the greater height function, which is 4, minus the lower height function, negative x squared plus 4, and then dx at the very end. That would be the volume of just one of these shells. And then, of course, to find the volume of the entire thing, you just integrate. This is where we find our bounds in terms of x. Well, if we're moving along the x direction, then it's the same principle, just that moving in a different axis. We move along the x-axis here. That means our bounds of integration should be vertical lines instead. I see one here that constricts the region on the left as x equals 0, and one that constricts the region on the right side as x equals 2. That means those are bounds of integration, which means that the volume using the shells method would be the integral from 0 to 2 of the volume of each of these shells, which is 2 pi multiplied by 3 minus x multiplied by 4 minus negative x squared plus 4, and then dx at the very end. That would be our volume in terms of shells. Okay, now that we have our formulas, the last thing we need to do is we just need to find which answer is the correct answer to our problem here. Let's look at the first one. For the washer's method, it's 0 to 4, that's correct, of pi multiplied by 3 minus the square root of 4 minus y squared minus 1 squared. This is effectively the same as what we have here, just they factored out a factor of pi from this entire formula. So this one might be correct. Let's look at 2 using the shells method. The integral from 0 to 2 of 2 pi times 3 minus x multiplied by 4 minus negative x squared plus 4, all of that in parentheses, with respect to x. That one is also correct. That one also matches our formula. So maybe this one is the correct answer here, but just to be sure, let us go check out the other ones. So we have, immediately off the bat, this is wrong. There should not be any instance of a 5 in this problem, so we know that B should be incorrect. And additionally, if we look in the second formula with shells, this radius should be 3 minus x and not x. That means that your radius would be this. But the radius that we want, or sorry, the radius that formula uses would be that. But the radius that we want is this. Right? So we know that this one's wrong right off the bat. Next one, right off the bat, we see our bounds of integration are incorrect in both cases. In fact, our variable of integration is wrong. This should be dy, that should be dx. So that one's wrong. That one's also wrong then. Now the last thing we need to look at is e. E almost looks correct, but remember, we defined this to be our bigger radius. We'll call that r big. And this is our r small. But if that's the case, then why is r small, or why is r big being subtracted from r small instead of the other way around? That doesn't make logical sense whatsoever. You would actually end up getting a negative radius or a negative area function here. That would be incorrect. And now let's look at this one. The same thing happens. They defined it as x minus 3, but in fact it should be 3 minus x. As we've seen, x in this case must always be less than or equal to 3. That means you end up still getting a negative volume and a negative area. That means that this answer choice E is incorrect. All we're left with is answer choice A as the correct answer. Welcome and welcome back, everybody. Thanks for joining me today as I cover question 23 of this problem set. The alternating series test shows that this infinite series here converges to a value of s. We can set the partial series of that same series to the nth term instead of to the infinite term. The problem asks us to find the smallest n using the estimation theorem for alternating series such that we can conclude that the error between the full series and the partial series must be less than that of 1 over 10 squared. Now, I'm not going to go too much into the conceptual part, but I'll talk a little bit about what the theorem is. And then if you're interested about why it is that way, you can look it up. The estimation theorem for alternating series states that if I'm given a partial series, which is from k equals 1 to the nth term of the a sub kth term, and I have the full series is the same thing from 1 to infinity of a sub k, my error between the full and the partial series should be less than the first term that I did not include in my series for the partial series, which is a sub k plus 1. That is the next term. Or sorry, not a sub k plus 1. That would be a sub n plus 1, the first term that I did not include in my partial series. Now, it makes pretty intuitive sense that your error should decrease as you increase the number of terms in your partial series, but if you want to look more specifically about why it's the next term, then feel free to do so, but I will not cover that in this video. We're just going to apply this principle here to solving this problem. That means that the error here should be less than this term, or so it should be less than or equal to this term, which means that this term here should be less than or equal to 1/100th, or 1/100th, which is our designated or desired error in this case. So the way that we would do this is we would find the a sub n plus 1 term. That would be negative 1 to the k n plus 1. And that would be over 1. That would be multiplied by 1 over the square root of 7 times k plus 1 in parentheses. That, as we have recognized, must be less than or equal to our desired error, which is 1 over 10 squared, or 1/100th. Now, the problem, or the theorem tells us that we're only looking for the error, which is always positive. Error is always positive, so we take the absolute value of this. That gets rid of our alternator here. So we're left with just 1 over the square root of 7k plus 1 must be less than or equal to 1 over 100. The first thing I will do is I'm going to raise everything to the negative 1 power. That gets rid of the fraction component. Then it becomes negative 7, square root of 7 times k plus 1. But the inequality here must change from less than equal to now to greater than 100. The reason for that is because if I have something like 1 over k, as k increases, this entire term decreases. That also means that if I have just k on its own, this evaluated as k increases will also increase. So in this case, the inequality kind of flips around if I flip around the fraction, which is why it turns from less than equal to into greater than. From here, we just square everything. 7 times k plus 1 must be greater than 10,000. 7k plus 7 must be greater than 10,000. 7k must be greater than 9,993. And then k must be greater than 9,993 over 7. Keep in mind that k in this case must be an integer since we're evaluating something related to a series. So let's see what 9,993 over 7 is. I have my calculator right now. That would be equal to, actually the k in this case must be greater than 1427.57. We're looking for the first term in which that satisfies this condition. And that would be answer choice B, or 1428. So the 1428th term is the first term in which the error is guaranteed to be less than 1 over 100th.
Welcome and welcome back, everybody. Thanks for joining me as we cover question 24. Given that the following series is a Taylor series for the function f of x centered at x equals 2, the value of the fifth derivative at that point is blah, 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 blah. All right. So let's go over what the form of a Taylor series looks like. And it's essentially just the sum of a bunch of different approximations at a point. If I have a function f of x, I can write that function f approximation of x that represents the best approximation of the function f of x at a certain point. Let's say instead of having it as a general x, you plug in some value of a. That a is pretty arbitrary, but that represents the x value at which or around which your function is centered. Your Taylor series looks like f of a, or the point itself at x equals a, plus the first derivative at a multiplied by x minus a, plus f double prime of a multiplied by x minus a squared, and that would be over 2 factorial, plus f triple prime of a over 3 factorial times x minus a cubed, and then plus so on and so forth. That means it would be equal to the sum of f to the f and the nth derivative of f centered at a multiplied by x minus a to the nth power over n factorial. With that being said, then we can compare it to this function directly because it is in fact a Taylor series as well. So this would be the series of 5 to the k over x k 5 to the k over k plus 3 factorial multiplied by x minus 2 to the 2k. Now the idea with these Taylor series is if you take the nth derivative of the Taylor series, all of the preceding terms should go away, and what you're left with is just f prime, or f of the nth derivative of a. That's all you're left with. Like let's take a look, for example, if we took the second derivative of this series. Both of these terms would go away, and you do the power rule twice on this term here. So what you're left with is just f double prime of a at that point, and then plus, what is it? F triple prime of a, and then some constant out in front. Of course, you still are left with the rest of the series, but the point being that you can extract the nth derivative at that point, depending on how many derivatives that you take. We can apply the same principle here. It's asking for the fifth derivative of the function. The fifth derivative can be approximated or can be represented by the fifth term, or technically the sixth term, in the Taylor series representing that function. So we need to find some value of k such that this degree here is equal to 5. Now you'll notice right off the bat, well, if we need to find some integer of k such that this is true, there is no integer of k, because the best that we can get is k is equal to 5 halves. But in a series, the most important thing is that the inputs of k that you have, they're never decimals, they're always integers. That means there's no value of k such that the fifth derivative can be a non-zero value. Because if it's 2k's, that means you have a term with degree 0, you have a term with degree 2, 4, 6, 8, and 10. You have no term with the degree of 5. that means there's no fifth derivative term present. That means that the fifth derivative of 2, represented by the Taylor series, should be equal to 0. Our best answer choice for this problem is E. Welcome and welcome back, everybody. Thanks for joining me as we cover question 25. Consider the series shown below. We can conclude one of the 5 statements shown below this. All right, so I think the best way to do this is just to work through each question or work through each possible answer choice and determine whether or not that answer choice has any validity. So we'll start with answer choice A. The series, okay, all right, not now. The series is convergent since as k approaches infinity, the terms of k reduce to 0. Right off the bat, we should probably cross this out as a possible answer choice because just because the terms approach 0 does not mean that the series converges. In fact, you look at something like the harmonic series, and you already know that this series converges. So we can cross off A off the list. Nothing is guaranteed by the terms approaching 0. This series is divergent by ratio test, since the limit as k approaches infinity of A over A sub k plus 1 over A sub k is equal to 1. All right, well, let's try to do that then. So we have the limits as k approaching infinity of k plus 1 over k plus 1 squared plus 2k plus 1 plus 3. Actually, I'm not going to do the ratio test. What you should observe is that as k approaches infinity, you can approximate this polynomial in the bottom to just be k squared, right? That means that the ratio between the numerator and the denominator is 1 over k. And then you have the sign of 1 over k out in front. Now again, as k approaches those large values, that means that the 1 over k in the sign gets very, very small as well. Then you can apply the small approximation theorem. The small angle approximation theorem, which says that if theta is less than 10 degrees, relatively about 10 degrees, then sine theta can be approximated as just the value of theta itself. So in this case, sine of 1 over k is obviously much, much smaller than 10 degrees at large values of k. So this sine of 1 over k becomes approximated as 1 over k. This series, where am I right now? This series is 1 over k squared for each term k. That means that every term decreases over time significantly from the previous term. That means that this, what the hell? That means that this one is false too, because we know from looking at this, and you can prove with the ratio test as well, but I'm not going to right now, that as k approaches infinity, these terms get smaller and smaller. That means the ratio between two consecutive terms is not equal to 1. Let's look at number 3. The series is divergent by limit comparison test with k over k squared. That turns into 1 over k. Now, this is actually where I got tripped up working over this the first time. You have to consider that sine of 1 over k can be approximated as 1 over k. That means that at large values of k, this entire term here obviously becomes 1 over k, since you can approximate the polynomial as just k squared. But then you have to incorporate the sine of 1 over k into this too. That's 1 over k. This becomes 1 over k squared at large values of k. That means that you cannot compare this to the 1 over k harmonic series. That means that C is false too. Now, D, the series is convergent by limit comparison test with the series of 1 over k squared. Now, this one might have some validity to it. I'm going to rewrite this down here. We have the limit or the sum of all terms k over k squared plus 2k plus 3 multiplied by 1 over sine of 1 over k. Let's look at this. We're comparing this with the series of 1 over k squared. As k starts at 1 and approaches infinity, the same. This term, again, I'm going to go over one more time.
this term, as k approaches infinity, can be approximated as 1 over k. But you have to still keep in mind that even though these terms are insignificant, they still play a factor into the denominator. The denominator, while it is approximated as k, still is a little bit greater than k. It's more like k plus a little bit of something else after that, right? And then the sign of 1 over k, we're just going to approximate that, keep that as 1 over k. That means that this is 1 over k squared, but kind of 1 over k squared. It's more like 1 over k squared plus a little bit of something. In fact, I'm going to write it out as this. 1 over k plus ... multiplied by k. If that's the case, then that's the case, then each of these terms must be less than each of the terms in 1 over k squared, because the denominator is just a little bit greater at large values of k than that of 1 over k squared. We already know that this series, by the p-series test, must converge. And if all the terms in this series are less than that in the terms in the 1 over k squared series, that means that all of these terms must converge in this series. So D might have some validity to it, but let's look at E just to make sure that we rule out any possible answer choice. The series is divergent by test for divergence since limit as k approaches infinity if a sub k does not exist. We can see that it most clearly does exist. Sine of 1 over k approaches 0 over time. And then k over k squared plus 2k plus 3, that approaches 0 over time. So you have two terms that are approaching 0 multiplied together. Obviously, their product will also approach 0. That means that E is incorrect, and all we're left with is D.